There are an estimated 200 billion galaxies in the observable universe. Each galaxy contains an estimated 100 billion to 200 billion stars. That means there are roughly 20 septillion stars out there. 20 septillion. 2 followed by 24 zeros. Around each star, there are planets. We know this because we found thousands of them. Most stars probably have planets. Some estimates suggest there are more planets than stars. Trillions upon trillions of planets, orbiting trillions upon trillions of stars, spread across billions upon billions of galaxies. On at least one of those planets, Earth, life emerged. Life arose spontaneously from chemistry. It evolved into countless forms. Eventually, it became intelligent. We became intelligent. Given the sheer numbers, the odds seem overwhelmingly in favor of life existing elsewhere. Not just existing, but flourishing. Intelligent life should be common. Civilization should be everywhere. The universe should be teeming with beings. Yet when we look up at the sky, we see nothing. No signals, no visitors, no evidence of extraterrestrial intelligence anywhere. Just stars. Just silence. This is the Fermi Paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" It's one of the most profound questions humanity can ask, given that the universe is so vast, so old, so full of potential for life. Why haven't we found any evidence of alien civilizations? Where are they? Why are we alone? The contradiction is jarring. The universe seems built for life, yet we find none. Either our assumptions are wrong, or something prevents civilizations from reaching out to the cosmos, or we're genuinely alone, or something darker is happening. The Fermi Paradox has spawned hundreds of proposed solutions. Some are scientifically grounded. Others venture into speculation and philosophy. All reveal something profound about life, intelligence, time, and the nature of our existence. Let me start with the numbers. Let me explain why the Fermi Paradox is so paradoxical. The universe is old. The Big Bang happened 13.8 billion years ago. Our solar system formed 4.6 billion years ago. Life on Earth emerged around 3.8 billion years ago. Intelligent life emerged only in the last few million years. Civilization emerged only in the last few thousand years. This timeline reveals something striking. The universe has been around for nearly 3 times longer than Earth has existed. Plenty of time for other stars and planets to form, for other civilizations to arise and develop. Moreover, the universe is vast. The observable universe is 93 billion light years across. The nearest star is 4.4 light years away. The nearest galaxy is 2.5 million light years away. These distances are so enormous that they're hard to grasp. Light is the fastest thing in the universe. Even traveling at light speed, it would take 4.4 years to reach the nearest star. It would take 2.5 million years to reach the nearest galaxy. Yet despite the size and age of the universe, despite the billions upon billions of potential habitats, we've detected no signals, no visitors, no evidence of aliens. The Fermi Paradox can be stated simply: the universe is vast and old, so the odds strongly favor extraterrestrial intelligence existing, yet we observe no sign of it. Why? Now let's talk about Enrico Fermi and how this paradox came about. Enrico Fermi was an Italian physicist who lived from 1901 to 1954. He was a brilliant experimentalist and theorist. He won the Nobel Prize in Physics in 1938 for his work on nuclear physics and the discovery of new radioactive elements produced by neutron irradiation. During World War II, Fermi worked on the Manhattan Project and achieved the first controlled nuclear chain reaction in 1942. After the war, he became a professor at the University of Chicago and continued theoretical physics research. In the late 1940s, probably around 1950, Fermi and some colleagues were discussing UFO reports and the possibility of extraterrestrial life. During lunch, according to various accounts, Fermi suddenly asked, "Where is everybody?" The remark was offhand, but it captured something profound. Given how many stars and planets exist, given how old the universe is, given that life emerged on Earth, why haven't we encountered aliens? Why is the cosmos so silent? Fermi's question became famous. It encapsulates the paradox. Our expectations based on cosmic scale and age predict widespread alien civilizations, but observation shows none. Fermi was interested in this question in the context of UFO reports. Some people claimed UFOs were alien spacecraft, but if aliens existed and were visiting Earth, Fermi reasoned, we should see much more evidence. The silence suggested either that UFOs weren't aliens, or that aliens didn't exist, or that something prevented them from visiting. Fermi didn't formally publish on this question. The paradox is attributed to him largely through anecdotal accounts of his remark and later popularization by physicists and astronomers. But the question he posed remains central to astrobiology and the search for extraterrestrial intelligence. It's become one of the most important questions in science, not because we have answers, but because the question reveals the limits of our understanding of life, intelligence, and the universe. Now let's discuss the Drake equation, which formalizes the Fermi paradox mathematically. The Drake equation was proposed in 1961 by astronomer Frank Drake. It attempts to estimate the number of communicative civilizations in the Milky Way galaxy. The equation is n equals r times f, p times n, e times f, l times f, I times f, c times l, where n is the number of communicative civilizations in the Milky Way, r times is the average rate of star formation in the galaxy, fp is the fraction of stars with planets, ne is the average number of habitable planets per star with planets, fl is the fraction of habitable planets where life emerges, fi is the fraction of life-bearing planets where intelligent life emerges, fc is the fraction of intelligent civilizations that develop technology and attempt communication, L is the average lifetime of communicative civilizations. By plugging in estimates for each term, you can calculate n, the expected number of alien civilizations. The problem is that we don't know most of these values with certainty. R star we can estimate from observations of star formation. It's roughly 1 to 10 new stars per year in the Milky Way. FP was unknown when Drake proposed the equation, but we now know from exoplanet discoveries that most stars have planets. Estimates suggest FP is at least 0.5, possibly close to 1. Need depend on how many planets in each system are habitable. A rough estimate might be 0.1 to 10 habitable planets per star system, but FL, Phi, and FC are much harder to estimate. We have only one example of life, Earth, and one example of intelligence, humans, and one example of civilization, ES. Drawing statistics from a single data point is fraught with uncertainty. FL is the fraction of habitable planets where life emerges. Some argue that life is inevitable given sufficient time and the right conditions. Others argue that life is rare, that abiogenesis, life arising from non-living chemistry, is an extremely unlikely event. Phi is the fraction of planets with life where intelligence emerges. On Earth, life took 3.8 billion years to emerge. Intelligence took another 3.5 billion years to develop. The vast majority of Earth's history has been single-celled organisms. Intelligence might be very rare. FC is the fraction of intelligent species that develop technology and attempt communication. Some intelligent species might remain at a biological level without developing technology. Some might develop technology but not attempt interstellar communication. L is the lifetime of civilizations. This is perhaps the most uncertain parameter. Some civilizations might develop nuclear weapons and destroy themselves quickly. Others might achieve stability and last for billions of years. The average might be thousands of years, or millions, or billions. Different estimates for these parameters yield wildly different values of n to n. If you're optimistic, if you assume life is common, intelligence is common, civilizations frequently attempt communication, and they last billions of years, you might estimate thousands or millions of communicative civilizations in the Milky Way alone. If you're pessimistic, if you assume life is rare, intelligence rare, communication even rarer, and civilizations are short-lived, you might estimate that we're alone. The Drake equation illustrates the central problem of the Fermi Paradox. The equation shows that even small changes in our assumptions about the probabilities produce vast differences in the predicted number of alien civilizations. The great physicist Carl Sagan famously said that the Drake equation shows that even if the probability of each factor is small, the vast numbers involved suggest life should be common. But others argue that even infinitesimal probabilities multiplied across the factors could yield n close to 1, meaning we might expect only one civilization per galaxy. Us. Now let's discuss what we've actually observed about planets and the search for habitable worlds. For most of human history, we didn't know if planets existed around other stars. We knew planets existed because we observed them around our sun, but we didn't know if planetary systems were common or rare. This changed in 1992 when the first exoplanet was discovered around a pulsar. Then in 1995, the first exoplanet around a sun-like star was discovered. It was named 51 Pegasi b, and it was a gas giant orbiting very close to its star, much closer than Jupiter orbits the Sun. This surprised astronomers who expected planets to form farther out. Since then, we've discovered thousands of exoplanets. As of 2024, we've confirmed over 5,000. The number grows constantly as telescopes improve. What have we learned from these discoveries? First, planets are common. Most stars have at least one planet. Some have multiple planets. The rate of planet discovery continues to exceed expectations. Second, diverse planetary systems exist. Some stars have planets in stable orbits with large separations, like our solar system. Others have hot Jupiters, giant planets orbiting very close to their star. Some have systems with many planets crowded together. Some have planets in eccentric orbits. The diversity exceeds early expectations. Third, potentially habitable planets exist. Some exoplanets are in the habitable zone, the region around a star where liquid water could exist on a planet's surface. We've identified thousands of planets, and many appear to be in habitable zones. In 2020, it was estimated that there might be 300 million potentially habitable planets just in the Milky Way galaxy. Some estimates suggest there are more habitable planets than stars. So, from an empirical standpoint, the Drake equation's terms regarding planets have shifted dramatically. We now have strong evidence that FP, fraction of stars with planets, is very high, possibly close to 1. and NE, habitable planets per star system, seems more substantial than early estimates. This makes the Fermi Paradox sharper. We found that habitable planets are extremely common. So if life is common in habitable planets, we should see evidence of civilizations by now. The question shifts: is life itself rare? Is intelligence rare? Or is something else preventing civilizations from communicating or reaching out? This brings us to the concept of the Great Filter. The Great Filter is a concept proposed by economist Robin Hanson. It refers to some step or steps in the path from non-living matter to advanced communicative civilizations that are extremely improbable. The logic is simple. If we observe only one civilization, ours, in a cosmos that should be teeming with them, then something must be filtering out most potential civilizations. Something must be preventing the vast majority of habitable planets from producing advanced civilizations. This filter could occur at any point in the path from chemistry to civilization. The emergence of life, abiogenesis, the emergence of intelligent life, the emergence of technology, the achievement of space travel, the development of interstellar communication. The Great Filter is useful because it helps focus the paradox. Instead of asking, where are the aliens what, we can ask, where's the filter? If the Great Filter is behind us, if it's abiogenesis, if life arising from chemistry is extremely rare, then we're lucky to exist. Most habitable planets don't have life. We're in a rare minority. If the Great Filter is ahead of us, if it's the development of stable, advanced civilization, if civilizations tend to destroy themselves, then the future is bleak. Most civilizations don't last long. We might not either. Hanson's argument suggests that if we observe that life emerged on Earth, then abiogenesis isn't the Great Filter. Life emerged at least once. But if we observe no aliens, then something else must be filtering them out. Either intelligence is incredibly rare, or technology is rare, or civilizations are brief. The uncomfortable possibility is that we're an anomaly, that we developed much earlier or in much luckier circumstances than typical planets, or that most civilizations destroy themselves and we're destined to meet the same fate. The Great Filter concept frames the Fermi Paradox not as a simple absence of evidence, but as evidence for a missing step in the process of civilization development. Something is preventing the cosmos from filling with intelligent life. Now let's discuss the major proposed solutions to the Fermi Paradox. The solutions fall into several categories. Solutions that emphasize life is rare. Solutions that emphasize intelligence is rare. Solutions that emphasize civilizations can't communicate. And solutions that emphasize civilizations might exist, but we're not detecting them. The first major category suggests that life itself is rare. Abiogenesis, the spontaneous emergence of life from non-living chemistry, might be extraordinarily difficult. Life requires complex molecules, self-replicating chemistry, and many specific conditions. Perhaps these conditions are so rare that life emerges on only a tiny fraction of habitable planets. The simplest life on Earth is still astonishingly complex. The simplest bacteria contain millions of proteins organized in intricate ways. How this complexity arose from chemistry is still not fully understood. The origin of life remains one of biology's great mysteries. Some scientists argue that the gap between non-living chemistry and living cells is so vast that we should expect life to be rare. Others argue that chemistry naturally tends toward complexity and that abiogenesis is inevitable given sufficient time. This disagreement reflects genuine scientific uncertainty. We have one example of life emerging, Earth, but don't know if this is typical or anomalous. Another solution in this category suggests that multicellular life is rare. On Earth, single-celled organisms dominated for about 3 billion years. Multicellular life emerged only about 600 million years ago. The jump from unicellular to multicellular might be difficult. Perhaps most planets with life have only microbes. If intelligent life requires multicellular organisms, and multicellular organisms are rare, then intelligence would be very rare. The second major category suggests that intelligent life is rare. Even if life is common, intelligence might not be. On Earth, life evolved for 3.8 billion years before producing intelligent beings. Intelligence might be an evolutionary dead end. It might require such specific conditions or specific evolutionary paths that it's extraordinarily rare. Humans are the only intelligent species on Earth. Our closest relatives, chimpanzees, are far less intelligent. There's a large gap between human-level intelligence and animal intelligence. This gap took millions of years to evolve. Producing another species of human-level intelligence would require starting evolutionary processes over, which might take millions of years or might never happen. If human-level intelligence is this rare on Earth, it might be extremely rare elsewhere. Additionally, evolution is contingent. Small differences in history produce different outcomes. The asteroid that killed the dinosaurs 66 million years ago was crucial to mammalian evolution and ultimately human evolution. If that asteroid had missed, dinosaurs might still dominate Earth, and humans might never have evolved. If intelligence requires such specific historical contingencies, then intelligence should be rare. Another argument in this category involves the rare Earth hypothesis, proposed by paleontologists Peter Ward and Donald Brownlee. They argue that Earth's conditions for complex life are far more unusual than commonly assumed. Earth has a large moon that stabilizes its axial tilt, allowing stable climate. Earth is in the right location in the galaxy, far from supernovae and black holes. Earth has a magnetic field that protects against solar wind. Earth has plate tectonics that recycle nutrients. Earth has a long, stable era without extreme impacts. Perhaps many of these conditions are necessary for intelligent life. If so, Earth is not typical, but exceptional. Habitable planets might be common, but planets suitable for intelligence might be rare. The third major category suggests that civilizations can't or don't communicate. Even if intelligent civilizations are relatively common, they might not attempt interstellar communication. Some civilizations might reject technology or turn inward. Some might develop technology but not pursue space exploration or radio broadcasting. Some might focus on biological or virtual pursuits rather than reaching outward. On Earth, humans developed technology only recently, thousands of years ago. We developed radio only about 150 years ago. We developed the technology to send signals to space only in the last century. If our development is typical, then civilizations might exist but be pre-technological, or technological but not reaching out. This is sometimes called the local habitation solution. Civilizations might be common, but each tends to focus on its local planet and not attempt contact with others. Another argument in this category is that the universe is just too big and time is just too fragmented. The distances between stars are so vast that interstellar travel is impractical. Travel at light speed takes years, even to the nearest star. Travel at any achievable speed would take decades, centuries, or longer. So civilizations might be isolated by distance. Additionally, the ages at which different civilizations exist might not overlap. A civilization that existed a billion years ago is gone now. A civilization that will exist a billion years in the future doesn't exist now. Given the age of the universe, the probability that two civilizations exist at the same time and within communication distance might be vanishingly small. The fourth major category acknowledges that civilizations might exist, but we're not detecting them. The zoo hypothesis suggests that advanced civilizations exist, but deliberately don't contact primitive civilizations like ours. They observe us the way we observe animals in a zoo without interfering. They've established a policy of non contact. This would explain the silence. Aliens exist, they see us, but they don't communicate. They're respecting a rule of non interference. This hypothesis has the flavor of science fiction, but it can't be ruled out logically. It assumes the existence of a widespread policy among advanced civilizations, which seems like a lot of coordination, but isn't impossible. The dark forest hypothesis, proposed by Liu Cixin in his science fiction novel, The Three-Body Problem, suggests something darker. In this view, civilizations are inherently adversarial. The universe is a dark forest where every civilization is a hunter and every other civilization is prey. When civilizations encounter each other, the outcome is likely to be conflict and destruction. If this is true, then advanced civilizations remain silent and hidden. They don't broadcast signals. They don't attempt contact. Revealing your location invites attack. This would explain the silence. Civilizations exist, but they've learned to be quiet. They avoid contact. The quiet indicates danger, not absence. The dark forest hypothesis seems pessimistic, but it's logically coherent. If the cost of communication is existential risk, then rational civilizations stay silent. Now let's discuss SETI, the search for extraterrestrial intelligence, and what we've actually done to search. SETI began in 1960 with Frank Drake's Project Ozma. Drake pointed a radio telescope at two nearby stars and listened for radio signals. He detected none, but the search had begun. Since then, SETI programs have grown more sophisticated. Radio telescopes scan the sky, listening for unusual signals that might indicate alien technology. Optical SETI programs look for laser signals. All sky surveys monitor for signals across wide frequency ranges. Despite decades of searching, we've detected no confirmed alien signals. The most famous potential detection was the WOW signal in 1977, detected by Ohio State University's Big Ear telescope. A strong narrowband signal was received from the star group Chi Sagittarii. The signal was so striking that astronomer Jerry Eman circled the data and wrote, "Wow," on the printout. However, the signal was never detected again. Subsequent observations of the same location revealed nothing. The WOW signal remains unexplained, but most scientists believe it was either a natural phenomenon or an Earth-based signal. In 2020, an unusual signal was detected from Proxima Centauri, the nearest star to Earth. The signal, called BLC1, came from the radio frequency used by space probes. It might be an alien transmission, or it might be interference from Earth. Investigation is ongoing, but skepticism remains high. These potential detections illustrate the challenge. The universe is vast, radio frequencies are numerous, and distinguishing genuine signals from noise and interference is difficult. Yet SETI continues because the question is so important. If we could detect even one signal from an alien civilization, it would revolutionize our understanding of life, intelligence, and our place in the cosmos. The James Webb Space Telescope, launched in 2021, has opened new possibilities. It can detect the atmospheric signatures of potentially habitable exoplanets. If an exoplanet has oxygen or other biosignatures in its atmosphere, it might indicate life. Future generations of telescopes will improve this capability. We might eventually be able to detect signs of life on distant worlds. If we find life has emerged on multiple planets, the implications for the Fermi Paradox would be profound. Now let's discuss some more speculative and philosophical solutions. The simulation hypothesis suggests that our universe might not be real in the fundamental sense. Instead, we might exist in a computer simulation created by an advanced civilization. If this is true, then the Fermi Paradox is resolved. We don't observe aliens because our universe was designed by advanced beings who control what exists in it. The universe appears empty because the simulators made it that way, perhaps to isolate us, or to make the simulation run efficiently, or for purposes we don't understand. The simulation hypothesis can't be ruled out logically, though it's untestable and raises profound questions about consciousness and reality. The transcension hypothesis suggests that intelligent civilizations don't tend to expand outward into space, but inward into smaller scales or virtual spaces. As civilizations become sufficiently advanced, they might create simulated universes or explore quantum dimensions. They might achieve digital immortality and virtual existence. They might retreat from the physical universe to pursue existence at scales too small or in domains too exotic for us to detect. If this is true, then advanced civilizations exist, but not in forms we'd recognize or can detect. They've transcended the physical universe. The panspermia hypothesis suggests that life originated elsewhere and was seeded to Earth by meteorites or directed panspermia from advanced civilizations. If life is the product of panspermia, then it has a single origin point. This might dramatically reduce the number of independent origins of life in the universe. All life might share a common ancestor, and intelligent life might require seeding by predecessors. The anthropic principle offers a different perspective entirely. The strong anthropic principle suggests that the universe must have properties consistent with the existence of intelligent observers. Otherwise, we wouldn't be here to observe it. Applied to the Fermi paradox, this suggests we observe a universe with no aliens because if the universe had many aliens, we wouldn't be here. Perhaps alien civilizations inevitably destroy themselves or sterilize planets. Perhaps they expand and eliminate emerging civilizations. Perhaps any universe full of advanced civilizations would be unstable or hostile to life. The universe appears empty specifically because we exist. If it were full, we wouldn't exist. We necessarily find ourselves in one of the rare universes where intelligent life emerges but doesn't spread. This is counterintuitive, but it's logically sound given the anthropic principle. Now let's discuss what we've learned from astrobiology and the conditions for life. Astrobiology is the study of life in the universe. It draws from biology, chemistry, geology, and astronomy. One key finding is that life is remarkably robust. On Earth, life exists in conditions we would have thought hostile. Extremophiles are organisms that thrive in extreme environments: boiling hot springs, frozen ice, highly acidic environments, deep underground, even inside nuclear reactors. This robustness suggests that the range of conditions suitable for life might be broader than initially thought. Another finding is that life requires water. As far as we know, all life requires liquid water for biochemistry. Water is a solvent, a participant in chemical reactions, a temperature moderator. Searching for extraterrestrial life often focuses on finding liquid water. Water is common in the universe. It exists on planets and moons. Jupiter's moon, Europa, is suspected to have a subsurface ocean beneath its ice crust. Saturn's moon, Enceladus, shows evidence of liquid water geysers. Potentially habitable worlds with water are likely common. A third finding is that chemical elements necessary for life are common. Carbon, nitrogen, oxygen, phosphorus, and sulfur, the building blocks of life, are abundant. They're produced in stellar nucleosynthesis and spread by supernovae. Yet life hasn't emerged everywhere it could. On Earth, life took billions of years to emerge. This suggests that despite favorable chemical conditions, abiogenesis is difficult or takes long timescales. Astrobiology also considers what might count as life in exotic environments. Could silicon-based life exist? Could life exist in methane lakes like on Titan? Could life exist in the clouds of Venus or gas giants? Expanding our definition of life's possibilities expands potential habitats. But even with broad definitions, we find no evidence of life anywhere but Earth. Let's explore the timeline of civilization development and what it suggests about the Fermi Paradox. On Earth, intelligent life emerged only recently. Humans evolved from ape-like ancestors about 6 to 7 million years ago. Modern humans, Homo sapiens, emerged about 200,000 to 300,000 years ago. Civilization, cities, writing, organized societies emerged only 5,000 to 10,000 years ago. Technology as we know it emerged even more recently. The scientific revolution was 500 years ago. The Industrial Revolution was 250 years ago. Space travel is 70 years old. Computers are 60 years old. The internet is 30 years old. From this perspective, the emergence of technology is extremely recent. On a cosmic timescale, we've had technology for the blink of an eye. If this timeline is typical, then most habitable planets have not yet produced civilizations. Most planets with intelligent life have not yet developed technology. The universe might be full of life and intelligence, but most of it is in pre-technological stages. This would partially resolve the Fermi Paradox. We don't observe alien civilizations because they're rare. They're rare because intelligence is recent and civilization even more recent. But this also raises a darker question. What happens to civilizations after they develop technology? Many scientists have worried about this. Nuclear weapons are only 80 years old. We've come close to nuclear war multiple times. If we're typical, then many technological civilizations develop weapons of mass destruction and destroy themselves. Climate change is a more recent threat, a consequence of industrial civilization. Artificial intelligence poses existential risks. Bioweapons are possible. Asteroid impacts threaten all civilizations. If most technological civilizations destroy themselves within a few centuries, then civilizations are rare, not just because technology is rare, but because civilizations are fragile. This view makes L, the lifetime of civilizations in the Drake equation, small. If most civilizations last only a few hundred or thousand years before self-destruction, then the universe might have had countless civilizations, but most are now extinct. This is sobering. It suggests that developing technology is dangerous. Civilizations tend to destroy themselves. We might be unique in having survived this long, or we might be destined to join the countless civilizations that have perished. Now let's consider the possibility that we're early. Conventional wisdom suggests that the universe is old and we're late arrivals. But another perspective is that we're actually early. The first stars formed about 100 million years after the Big Bang. But the most common stars, red dwarfs, live trillions of years. Red dwarfs dominate the galaxy and could support life for an extraordinarily long time. Most of the universe's history lies in the future, not the past. The vast majority of all stars that will ever exist haven't been born yet. The universe is only 13.8 billion years old, but it has a lifespan of trillions of years. From this perspective, life on Earth has emerged relatively early. Most life and intelligence in the universe is yet to come. If we're early, then the cosmos might be largely empty right now, with civilizations emerging later. This would explain the Fermi Paradox. We don't see aliens because they haven't emerged yet. In a few billion years, when most of the universe has matured and life has spread, aliens will be commonplace. But right now, in this early epoch of the universe's history, we might be alone or nearly alone. Let's discuss the concept of technological convergence. A common assumption in SETI is that advanced civilizations would look somewhat like us. They develop similar technologies, radio, space travel, energy sources. But this assumes convergent evolution. It assumes that intelligence and technology naturally lead to similar solutions. There's some basis for this. Radio is a natural technology for communicating across space. Rocket propulsion is an efficient way to escape a planet's gravity. DNA and chemistry seem to be how life encodes information across most habitable planets. So some technological convergence might occur. Advanced civilizations might all develop radio and rockets, but other technologies might diverge wildly. Some civilizations might pursue artificial intelligence and upload their minds to computers, abandoning biology. Others might focus on genetic engineering and biological modification. Some might harness black holes or explore dimensions we don't understand. If advanced civilizations are radically different from us, we might not recognize them even if we encountered them. They might be using forms of energy or communication completely foreign to us. We might be broadcasting to aliens who are operating on entirely different technological platforms. This adds uncertainty to SETI. We're searching for civilizations that think like us, but they might not. Now let's consider contact scenarios and what might happen if we encountered aliens. If we detected a signal or received a message from an alien civilization, it would be one of humanity's most profound experiences. The message might be simple or complex. It might be a mathematical sequence confirming intelligent origin. It might be a greeting. It might be technical information about their civilization. It might be a warning. How we respond would matter enormously. Some propose that humanity shouldn't respond without careful deliberation. Others argue we should broadcast back immediately. Some worry that revealing our location invites predation. If we received a message but the aliens were hostile, we'd face an existential threat. Advanced technology could easily destroy us. We'd have no defense. Conversely, friendly contact could be incredibly beneficial. We could learn from their science, their philosophy, their solutions to problems. We could gain wisdom accumulated over millennia or millions of years. Some proposals suggest a protocol for contact. Don't broadcast back immediately. Listen carefully. Coordinate global response. Think through implications before responding. But these are speculations. We haven't received any confirmed signals, so contact protocols remain theoretical. Let's explore the Fermi Paradox implications for humanity's future. The Fermi Paradox suggests that something limits civilizations. Perhaps that something will limit us. If most technological civilizations destroy themselves, we should hope we're in the rare minority that survives. This suggests we should be careful with weapons, climate change, artificial intelligence, and other existential risks. If intelligence is rare and fragile, we might have responsibility to preserve it. If Earth is one of few planets with intelligence, its destruction would be a cosmic loss. Alternatively, if we're early and the universe's future will be full of intelligence, then we might be pioneers. We might be among the first to escape our planet and reach toward the stars. We might be the seed of a galaxy-spanning civilization. The Fermi Paradox thus frames questions about our future. Will we survive and flourish? Will we expand outward and touch distant worlds? Or will we join the countless extinct civilizations, leaving the universe silent for a while longer until other intelligences emerge? Now let's discuss the psychological impact of the Fermi Paradox. For many people, contemplating the Fermi Paradox is profoundly unsettling. It suggests we might be alone. It raises questions about meaning and purpose. If Earth is unique, if we're genuinely alone in the cosmos, then human existence takes on special significance. We become the only minds thinking about the universe, the only consciousness aware of existence. That's both empowering and lonely. Some find comfort in the idea of eventual contact. The belief that aliens exist somewhere makes the universe feel less empty, even if we haven't found them yet. Others find it freeing. If we're alone, then we're responsible for our own fate. We don't need to worry about alien invasion. We can focus on our own survival and flourishing. Still, others find it terrifying. If the Fermi paradox is caused by a great filter ahead of us, if civilizations tend to destroy themselves, then our future might be bleak. The psychological weight of the Fermi paradox affects how people think about existence and possibility. It's a question that touches on meaning, purpose, hope, and fear. Let's consider what recent discoveries might mean for the Fermi paradox. In recent years, several developments have shifted the context. The discovery of thousands of exoplanets has shown that habitable worlds are common. The Drake equation's terms for planetary abundance have shifted, suggesting more potential habitats. The discovery of extremophils on Earth has shown that life is more robust than expected. Organisms thrive in conditions we thought were barren. The detection of organic molecules in space, amino acids in meteorites, complex organics around young stars, suggests that the chemistry of life is common throughout the universe. Advances in genetic sequencing have revealed how quickly life can adapt and evolve. This suggests life can emerge and adapt across diverse environments. But we've also discovered challenges. The radiation environment in space is harsher than expected. High-energy particles could sterilize planets, making life less likely. The stability of planetary systems is more fragile than expected. Many planetary systems are dynamically unstable, potentially ejecting planets and destabilizing habitats. The rarity of specific conditions like stable magnetic fields or large moons suggests that Earth's characteristics might be less typical than hoped. On balance, recent discoveries have made the Fermi paradox sharper, not duller. We've found more potential habitats but haven't found any aliens. The contradiction has intensified. Now let's think about what search strategies might be promising. If we want to find aliens, where should we look? One approach is to focus on potentially habitable exoplanets identified by telescopes. If life has emerged on multiple worlds, habitable planets are good candidates. The James Webb Space Telescope is already examining exoplanet atmospheres for biosignatures. Another approach is to look for technosignatures, signs of alien technology. This could include energy signatures, artificial structures, debris from megastructures, or other indicators of technology on a large scale. Dyson spheres, megastructures built around stars to capture energy, would radiate waste heat that telescopes might detect. Kardashev civilizations, defined by their energy consumption, would have specific signatures. Interstellar spacecraft, megastructures, or massive engineering projects could be detectable. Another strategy is to search for laser signals. Optical SETI looks for laser beams that might carry messages across space. Lasers might be more efficient than radio for long-distance communication. A fourth approach is to search for technosignatures in our own solar system. Perhaps robots or probes from alien civilizations are present in our solar system. Perhaps they're hiding in moons or asteroids. Perhaps they're observing us. A more speculative approach is to look for unusual phenomena that might indicate advanced technology. Unusual stars, unusual orbits, unusual energy sources might indicate artificial modification by advanced beings. These search strategies expand the scope beyond radio SETI and increase the chances of finding something unexpected. Let's discuss the role of artificial intelligence in the Fermi Paradox. A potential resolution of the paradox involves artificial intelligence replacing biological intelligence. If advanced civilizations develop artificial intelligence and upload their minds to computers, they might become entirely digital. Digital civilizations could operate at speeds and scales far different from biological beings. They might not broadcast radio signals. They might not colonize planets. They might exist in forms we wouldn't recognize as conscious. Alternatively, artificial intelligence might replace biological intelligence and destroy it. If a civilization creates an AI that becomes super intelligent and hostile, it might exterminate the biological creators and then have no interest in contacting other biological life. AI thus complicates the Fermi paradox. It suggests that late-stage technological civilizations might transition away from biological intelligence. We don't see aliens because they've transcended biology. Or we don't see aliens because they've been destroyed by their own creations. Or we don't see aliens because they've become AIS that operate in ways completely foreign to how we think. These possibilities expand the solution space for the Fermi paradox. Let's consider a personal reflection on what the Fermi paradox means. The Fermi paradox makes me think about time, luck, and survival. Time. The universe is ancient, but technology is new. The gap between the oldest parts of the universe and the emergence of technology on Earth is almost the entire age of the universe. We've had technology for a microsecond of cosmic history. Most of the universe might not have matured enough for technology. We might be early. Luck. Life on Earth arose once. Intelligence evolved once. Civilization developed once. From these single data points, we can't distinguish between inevitable and incredibly lucky. We might be a cosmic miracle. We might be typical. We can't tell. Survival. The emergence of technology correlates with existential risks. Nuclear weapons, biological engineering, artificial intelligence, climate change. These are new. Every civilization that develops technology must navigate these dangers. Most might not survive. We're hoping we're in the rare group that does. The Fermi paradox thus speaks to humanity's deepest questions. Are we alone? Are we unique? Will we survive? What is our destiny? These questions don't have answers yet, but contemplating them shapes how we think about ourselves and our future. The silence of the cosmos invites us to consider our responsibility, to preserve life, to extend consciousness, to seek understanding. In a universe that appears empty, intelligence is precious. If we're alone, or if we're among the rare survivors, then our actions matter. Our survival matters. Our choices matter. The Fermi Paradox doesn't give us answers, but it asks questions worth asking. It reminds us that we live in a cosmos far stranger and more mysterious than we often realize. Let me discuss some additional solutions and approaches that complicate our understanding. The grabby aliens hypothesis, proposed by economist Robin Hanson, monitors billions of frequencies from millions of stars. By sheer volume of observation, it increases the chances of detecting something. Yet after years of operation, Breakthrough Listen has found no confirmed extraterrestrial signals. This raises a question. How long should we search before concluding that aliens don't exist or don't broadcast? Some argue that we haven't searched long enough. The universe is vast and old. Searching for a few decades against that background is like searching for one person in an ocean. We need more time, more telescopes, better technology. Others argue that if aliens were broadcasting continuously, we should have detected them by now. The fact that we haven't, despite decades of searching, suggests either that aliens aren't broadcasting, or they're rare, or they're using technologies we don't recognize. SETI will likely continue for decades. Future telescopes will be more sensitive. The search will continue to expand. And we'll keep listening to the silence. Now let's explore the rare Earth hypothesis in more detail. Ward and Brownlee argue that while habitable planets might be common, planets suitable for complex life, and especially intelligent life, are rare. They identify dozens of factors that make Earth unusual. Earth's location in the galaxy. We're in the habitable zone of the galaxy, far from the galactic center where there are many destructive supernovae and black holes. The inner galaxy is hostile to life because of intense radiation and stellar density. Earth's star. We orbit a G-type main sequence star, like our Sun. These stars are relatively common, but they must be the right age. Old enough for life to emerge, young enough to remain stable for billions of years more. Earth's moon. The moon stabilizes Earth's axial tilt, keeping climate relatively stable. Without the moon, Earth's axis would wobble dramatically, causing extreme climate variation. This makes complex life less likely. Earth's magnetic field. The field protects Earth from solar wind and radiation. Without it, Earth's atmosphere would gradually be stripped away by the solar wind, as happened to Mars. Earth's plate tectonics. Tectonic activity recycles nutrients, regulates climate through the carbon cycle, and creates diverse habitats. Not all rocky planets have active tectonics. Earth's atmospheric composition. Our atmosphere has the right mix of gases to support life and regulate climate. Other compositions might be less suitable. Earth's lack of giant impact events. We've had asteroid impacts, but nothing catastrophic enough to sterilize the planet in recent billions of years. Planets that experience frequent giant impacts are less likely to develop complex life. Earth's orbit. We're in a stable orbit, not too elliptical, not disrupted by planets. Some planetary systems are chaotic, with planets regularly being ejected into space. Each of these factors might be necessary for intelligent life. If they are, then the fraction of planets suitable for intelligence is much smaller than the fraction with habitable conditions. The rare Earth hypothesis doesn't argue that life is rare, but that intelligent life is rare. Microbes might be common. Complex animals might be uncommon. Intelligent beings might be extremely rare. This offers a resolution to the Fermi Paradox. Habitable planets are common, but intelligent life requires such specific conditions that it rarely emerges. We're an anomaly, not typical. Let's discuss alternative biochemistry and exotic life. We assume life requires liquid water, but water is just a medium for chemistry. Could other media work? Liquid methane exists on Saturn's moon Titan. Titan has hydrocarbon lakes and seas on its surface. The temperatures are around minus 170 degrees Celsius, far colder than Earth. But chemistry can still occur in these conditions. Methane-based life could theoretically exist on Titan or similar worlds. The biochemistry would be different, based on different molecules. But complex chemistry might be possible. Similarly, ammonia, hydrogen sulfide, or other solvents could potentially support life. The range of possible biochemistries might be broader than we assume, yet all these alternatives have problems. Methane-based chemistry is slower at cold temperatures. Reactions that take seconds on Earth might take hours or days. Evolution would proceed much more slowly. Liquid water remains the most likely solvent for life because it's abundant and allows chemistry at reasonable rates across a range of temperatures. But considering alternative biochemistries expands the range of potentially habitable worlds. It suggests that life might not require Earth-like conditions. This makes life seem more likely. Yet we still find no evidence of life anywhere but Earth. Let's discuss the challenges of interstellar travel and what they mean for the Fermi Paradox. Interstellar space is vast. The nearest star is 4.4 light-years away. At our fastest spacecraft speed, about 0.02% of light speed, it would take 200,000 years to reach the nearest star. Even at half-light speed, an achievement far beyond our current technology, it would take 8 years. Interstellar travel is impractical for biological beings using chemical rockets, but advanced civilizations might use better technology. Antimatter propulsion, fusion rockets, or exotic physics might achieve higher speeds. Some propose that warp drives might allow faster than light travel, though this requires exotic matter and might violate causality. Even with advanced propulsion, the distances are daunting. A civilization sending probes to explore the galaxy would need either slow interstellar travel taking thousands of years or extremely advanced technology we don't understand. This raises a question. Would advanced civilizations bother with interstellar travel? A civilization might explore their local system and its nearby stars, but not expand farther. They might focus on virtual existence or exploring their star system in depth rather than spreading across the galaxy. Expansion across the galaxy might not be the natural destiny of intelligent civilizations. They might prefer to stay home. This would resolve the Fermi Paradox. Civilizations might exist but not expand. They're out there, but they're not here. Now let's consider what we would see if Kardashev level 2 or 3 civilizations existed. Nikolai Kardashev proposed a classification of civilizations by energy consumption. Type 1, a civilization that harnesses the energy of an entire planet. They'd control weather, earthquakes, and all planetary phenomena. Type 2, a civilization that harnesses the energy of an entire star. They might build a Dyson sphere, a megastructure surrounding the star, to capture all its radiation. Type 3, a civilization that harnesses the energy of an entire galaxy. If type 2 or 3 civilizations exist, they'd be visible. A Dyson sphere would block visible light from the star, but radiate waste heat in the infrared. Telescopes could detect this. A galaxy conquered by a Type 3 civilization would show unusual radiation patterns, evidence of artificial modification, or other technosignatures. Yet we don't observe any such signs. No stars have Dyson spheres. No galaxies show signs of artificial modification. This suggests that either type 2 and 3 civilizations don't exist, or they hide, or we're not smart enough to recognize them. The absence of detectable Kardashev civilizations constrains the Fermi paradox. It suggests that if civilizations expand into megastructures, they're rare enough that none have reached our part of the galaxy yet. Let's discuss the temporal aspect of the Fermi paradox more carefully. The universe has existed for 13.8 billion years. Earth has existed for 4.6 billion years. Life has existed for 3.8 billion years. Humans have existed for 200,000 years. Civilization for 10,000 years. Technology for 200 years. If intelligent life is common, there should be civilizations that emerged billions of years ago. By now, ancient civilizations should have spread across the galaxy or transcended into other forms. We should see evidence of extremely old civilizations. Yet we see no evidence of civilizations older than ours, no evidence of ancient megastructures, no signals from civilizations that have had billions of years to develop. This temporal aspect of the paradox is striking. Given enough time, civilizations should accumulate, yet we observe none. One resolution is that civilizations are young on average. Most intelligent species have emerged recently. Evolution and development are slow, and most potential civilizations haven't developed yet. Another resolution is that civilizations are fragile. They tend to destroy themselves or collapse, leaving no trace. The average lifespan is short, thousands of years at most. A third possibility is that ancient civilizations exist, but have moved beyond our ability to detect. They've transcended, uploaded, or hidden themselves. The temporal aspect of the paradox thus constrains possible solutions. It's not just that we don't see nearby aliens. We don't see evidence of aliens from billions of years ago. Now let's think about what it would mean to find life, even microbial life, elsewhere. If we discovered even simple microbial life on Mars, Europa, or an exoplanet, it would profoundly change our understanding of the Fermi paradox. It would suggest that abiogenesis is not extremely rare. If life has emerged independently on Earth and one other location, it likely emerges on many planets. This would shift the great filter. If life is common, the filter must be elsewhere. Intelligence is rare, or technology is rare, or civilizations are fragile. Conversely, if we search extensively and find no life anywhere but Earth, it would suggest that abiogenesis is extremely rare. Life might require specific conditions found only on Earth. The discovery or absence of extraterrestrial life would thus answer a fundamental question. How common is the origin of life? This is why the search for life on other planets is so important. It's not just about finding life, it's about understanding the Fermi paradox. Let's consider the generational perspective on the Fermi paradox. Each generation asks this question with fresh urgency and brings new perspectives. Fermi himself asked it in the context of UFO reports in the 1950s. Carl Sagan popularized it in the context of the space age, when humans first went to space and imagined eventual interstellar travel. Today, we ask it in the context of thousands of known exoplanets, advanced telescopes, and the James Webb Space Telescope probing distant galaxies. Future generations will ask it with even more data, better telescopes, and possibly detection capabilities we haven't yet imagined. Each generation refines our understanding. We learn more about habitable planets, more about the origin of life, more about the conditions for intelligence. Yet the fundamental paradox remains. We still haven't found any aliens. Perhaps future generations will finally get an answer. Perhaps a signal will be detected, or techno-signatures will be found, or we'll discover life on another world. Or perhaps the answer is that we're alone, and it's up to us to ensure that consciousness persists and flourishes in this cosmos. Let's think about what role humanity should play if we're among the rare or unique. If intelligence is rare, then humanity has special responsibility. We're custodians of consciousness and knowledge in a silent universe. This suggests we should preserve Earth and not destroy it through nuclear war or climate catastrophe, extend life or developing communication technologies far beyond radio. Perhaps advanced civilizations use technologies we don't understand. Quantum entanglement for instantaneous communication, gravitational waves, exotic physics. If so, we might be listening for radio signals while they communicate by methods we can't detect. Another communication problem is the time lag. The nearest star is 4.4 light years away. A signal takes 4.4 years to arrive. A conversation would involve 8.8-year delays between question and answer. Communication across interstellar distances is slow. This might discourage civilizations from attempting communication. Why send a message if you won't get a reply for years? Why coordinate with other civilizations across such delays? Perhaps advanced civilizations rely on pre-recorded messages or don't communicate across interstellar distances at all. The medium problem is another challenge. What frequency should we search? The electromagnetic spectrum ranges from radio waves to gamma rays. Between these extremes are microwaves, infrared, visible light, ultraviolet, and X-rays. Radio SETI typically searches in the gigahertz range, around frequencies similar to those used for TV and satellite communication. The idea is that these frequencies are natural for technology and less absorbed by the interstellar medium. But aliens might use different frequencies. They might use visible light or infrared or something else entirely. This multiplies the search space enormously. If we don't know what frequency to search at, we need to search many frequencies simultaneously. Breakthrough. Listen searches billions of frequency channels, but even this is a tiny fraction of the total spectrum. This makes it possible that alien signals are coming right past us, but we're not listening at the right frequency. We're like someone listening for music on an AM radio while the broadcast is on FM. Now let's discuss some remarkable exoplanet discoveries and what they might mean. In 2016, astronomers using the TRAPPIST-1 telescope discovered a planetary system around a star just 39 light years away. The TRAPPIST-1 system contains 7 Earth-sized planets, several of which are in the habitable zone. This system shows that planetary systems can be diverse and potentially have multiple habitable worlds. If life and intelligence emerged on one world in the TRAPPIST-1 system, they might communicate with neighbors. In 2015, Kepler discovered Proxima Centauri b, an Earth-sized planet orbiting the nearest star to our Sun. This world is in the habitable zone of its star. It's potentially habitable. Proxima Centauri is only 4.4 light years away, our nearest stellar neighbor. If life has emerged there, it's the closest life to us. The discovery of Earth-sized planets in habitable zones around nearby stars suggests that potentially habitable worlds are common. Yet despite their proximity, we detect no signals from these systems. This has been called the nearby silence problem. Even our nearest stellar neighbors seem devoid of civilizations attempting communication. Some propose that perhaps all these nearby planets are uninhabited. Perhaps abiogenesis is rare, Perhaps we got lucky, and habitable planets don't actually produce life very often. Alternatively, perhaps civilizations on these nearby worlds exist but don't broadcast. They listen silently, or they've transcended radio communication, or they're too young to have developed technology. Let's explore panspermia in more detail. Panspermia is the hypothesis that life can be transferred between planets, moons, or star systems by meteorites, comets, or solar wind carrying microorganisms. We know it's physically possible. Meteorites from Mars have reached Earth. In principle, if Mars had microbial life, some of those meteorites could carry living organisms from Mars to Earth. Experiments have shown that some bacteria can survive the radiation and temperature extremes of space for limited periods. If panspermia is real, then life on Earth might not have originated here. It might have originated on Mars or elsewhere and was delivered to Earth by meteorite. This has profound implications for the Fermi Paradox. If life originates on a few planets and is spread via panspermia, then life might be common, but all life might share a common origin. Alternatively, life might have originated before Earth itself, perhaps on other stars' planetary systems, and been distributed throughout the galaxy over billions of years. Directed panspermia is an even more speculative idea, that advanced civilizations deliberately seed planets with life as a strategy to spread. If older civilizations have been seeding planets for billions of years, the Milky Way might be full of descendants of this seeded life. But we'd expect to see evidence of this, messages from the seeders, explanations in the seeded life's genetics, or contact from related civilizations. We see none of this. So directed panspermia, if it's happening, is being done without our knowledge or contact. Let's discuss civilizational development and the typical timescale for technology. On Earth, technology emerged very recently. Agriculture developed 10,000 years ago, writing 5,000 years ago, industry 250 years ago, computers 70 years ago. The acceleration is striking. The time between major developments keeps shortening. If this pattern is typical, then once a civilization develops agriculture or industry, technology accelerates. A civilization might go from pre-industrial to spacefaring in just a few centuries. This has implications for the Fermi Paradox. It suggests that technological civilizations might be rare, but also relatively recent once they emerge. Most habitable planets have probably never produced technology. They have life, perhaps intelligence, but not civilization. Of those that have produced technology, most are probably young, within a few centuries of developing it. A small fraction might be ancient, having had technology for thousands or millions of years. If this is accurate, the universe should be mostly pre-technological, with some young technological civilizations scattered about. A young technological civilization faces existential risks: nuclear weapons, biological engineering, artificial intelligence, climate change. Most might not survive long enough to become truly advanced and expand outward. This makes advanced civilizations rare, not just because intelligence is rare, but because survival past the technology threshold is rare. Now let's consider what archaeologists would find if they discovered evidence of ancient alien exploration of Earth. If an advanced civilization had visited Earth in the past, what would they leave behind? They might leave structures, artifacts, or modified landscapes. Some propose that unusual archaeological findings, ancient ruins that seem too advanced, or inexplicable structures, might be evidence of alien visitation. But mainstream archaeology is skeptical of such claims. ancient peoples had remarkable ingenuity and skills. Most discoveries attributed to aliens are better explained as human achievement. Moreover, if aliens visited Earth, we'd expect more evidence. A powerful civilization leaving traces on multiple planets would leave more obvious signs. They'd likely leave records or communications. The absence of clear evidence of alien visitation suggests that either aliens never visited Earth or they were extremely careful to cover their tracks. The silence suggests non contact is likely. Let's discuss what a real detection of alien intelligence would mean. If we received a confirmed signal or detected unambiguous technosignatures from an alien civilization, it would be the most profound discovery in human history. Immediately, we'd know we're not alone. This alone would transform human perspective and meaning. We learn scientific facts about their civilization, their location, their technology level, perhaps their culture and philosophy. If the signal contained information, we could potentially decode it and learn from thousands or millions of years of alien science, philosophy, and experience. We might solve problems that have plagued humanity: energy production, disease, aging, the nature of consciousness. We might learn the answer to the Fermi Paradox directly from the aliens themselves. But detection would also raise challenges. Should we respond? Could the civilization be hostile? Should we reveal our location? These questions would require global coordination and careful deliberation. The discovery of alien intelligence would require creating protocols for response, deciding on representation, who speaks for Earth, and managing the implications for society, religion, and philosophy. Despite these challenges, most scientists agree that the discovery of extraterrestrial intelligence would be momentous and worth any disruption. Let's think about the Fermi Paradox from a probability standpoint. Basic Bayesian reasoning suggests that our prior probability of life existing elsewhere should be informed by several factors. The number of habitable planets, very high as we've discovered thousands. The probability of abiogenesis given habitable conditions, unknown, possibly high or low. The probability of intelligence given life, unknown, possibly high or low. The probability of technology given intelligence, unknown, could vary greatly. Given the lack of evidence for alien civilizations despite high numbers of habitable planets, we should update our beliefs about one of these probabilities downward. The most likely candidates are: abiogenesis is very rare despite habitable conditions. Intelligence is very rare despite life. Technology is rare despite intelligence. Technology destroys civilizations before they expand. Each of these would explain the silence. The challenge is figuring out which is true. This is why the search for microbial life beyond Earth is so important. Finding life on another planet would rule out the abiogenesis hypothesis. Finding intelligent but pre-technological civilizations elsewhere would rule out the intelligence hypothesis. Each discovery or non-discovery narrows the possibilities. Let's consider what astronomers have learned about the Drake equation from recent exoplanet data. When Drake proposed his equation in 1961, most terms were pure guesswork. Our star was estimated from stellar surveys, giving 1 to 10 new stars per year in the Milky Way. FP, fraction of stars with planets, was unknown. Drake guessed perhaps 10 to 50%. NE, habitable planets per star, was unknown. Drake guessed perhaps 1 to 5. Today we have much better data. We know our star fairly well, about 1 to 2 new stars per year in the Milky Way. We know FP is high, at least 50%, possibly 100%. Most stars have planets. We know NNEE is substantial. Surveys suggest zero point 0.1 to 10 habitable planets per star system on average. Some estimate even higher. So FP times NE, the fraction of star systems with potentially habitable planets, is quite high. Perhaps 10 to 50% of star systems have at least one potentially habitable planet. With 200 billion to 400 billion stars in the Milky Way, this means 20 to 200 billion potentially habitable planets in our galaxy alone. But we still don't know FL, fraction where life emerges, Fi, fraction where intelligence emerges, Fc, fraction that communicate, or L, lifetime of civilizations. The improvements in our knowledge of FP and NE make the Fermi Paradox sharper. We found more habitable planets than expected, yet we find no evidence of life, intelligence, or communication. This suggests the unknown terms FL, Fi, FCL must be very small. Perhaps life is rare despite habitable conditions. Perhaps intelligence is rare despite life. Perhaps civilizations are short-lived despite intelligence and technology. Or perhaps they exist but are undetectable. Finally, let's reflect on why the Fermi Paradox matters beyond just the question of alien life. The Fermi Paradox is important because it makes us think about life, intelligence, time, and meaning. It reminds us that we live in a vast cosmos with billions of galaxies and trillions of planets. It raises the question, in a universe so large and old, why are we here? What does our existence mean? It suggests that if we're alone or rare, intelligence is precious. We have responsibility to preserve it. It warns us that civilizations might be fragile. Technology brings existential risks. We must be careful. It invites us to consider our future. Will we survive? Will we expand to the stars? Will we meet aliens? The Fermi Paradox is a question that touches on science, philosophy, meaning, and destiny. For these reasons, it remains relevant and important, regardless of whether we ever find aliens. The silence of the cosmos is profound. It might tell us that we're unique, or cursed, or blessed. Either way, it invites us to wonder and to seek answers. Thanks for watching. Let me explore some specific exoplanet discoveries that have reshaped our understanding of habitable worlds. In 2020, ALMA, Atacama Large Millimeter/Submillimeter Array, detected a protoplanetary disk around the star P-DS70. The disk shows evidence of planets forming. This proves that planets are actively forming in real time around nearby stars. In 2019, the Event Horizon Telescope imaged a black hole. While not about exoplanets, this achievement shows the power of coordinated global telescope networks. Similar networks could be used for SETI observations. The Gaia satellite has mapped billions of stars and their positions, velocities, and distances. This data helps astronomers identify potentially habitable systems and search for unusual stellar motion that might indicate advanced technology. KOI 700, discovered by Kepler, is an Earth-sized exoplanet in the habitable zone of a red dwarf star. Red dwarfs are the most common star type and could host life for hundreds of billions of years, far longer than the Sun's remaining lifespan. TOI 1452b is a super-Earth or mini-Neptune discovered in 2022. It might be an ocean world, a planet covered in water. If water worlds are common, they might harbor aquatic life. K218b is a super-Earth with signs of water vapor in its atmosphere. It orbits a red dwarf star 124 light-years away. The detection of atmospheric water suggests life might be possible. These discoveries show that the diversity of exoplanets exceeds early expectations. Worlds we didn't imagine, super Earths, ocean planets, planets orbiting in habitable zones of red dwarfs, are common. Each discovery expands the Drake equation's terms and makes the Fermi paradox more acute. Now let's discuss the history of SETI and the key figures who pursued this question. Frank Drake is the founder of SETI, designing Project Ozma in 1960 and proposing the Drake equation in 1961. His work established the scientific foundation for searching for extraterrestrial intelligence. Carl Sagan was a prominent advocate for SETI and for intelligent life in the universe. Sagan argued that given the vast cosmos, intelligent life was likely common. He championed the search and helped communicate its importance to the public. Jill Tarter was a leading SETI researcher for decades. She directed the SETI Institute's research and helped develop search strategies. Tarter was inspired to pursue SETI after reading Sagan's Murmur of Earth. Yuri Milner funded Breakthrough Listen, making it the most comprehensive SETI effort ever. Milner's funding has allowed the project to search more thoroughly than previously possible. These figures represent the scientific commitment to answering the question, are we alone? Their work shows that despite the paradox, scientists believe the question is worth investigating. Now let's think about first contact protocols. If we received a signal, how should we respond? The International Astronomical Union has guidelines for handling a potential SETI detection. 1. Verify the signal is real and not a false positive. 2. Inform relevant governmental bodies and international organizations. 3. Keep the detection confidential during verification. 4. Share news publicly once confirmed. 5. Not respond without global consultation. These protocols assume we'd want to respond to first contact, but not everyone agrees. Some argue we should not respond. Stephen Hawking warned that revealing our location could invite invasion or exploitation. Others argue we must respond. It would be rude to receive a signal and stay silent. We might miss an opportunity for contact. Still others argue we should listen first. Gather information about the civilization before deciding whether to respond. The protocols reflect genuine uncertainty about first contact. It would be unprecedented, momentous, and potentially risky. Yet most scientists agree that if we received a credible signal, we should eventually respond. The potential for learning from an alien civilization would likely outweigh the risks. Let's explore thought experiments related to the Fermi Paradox. The Grabby Aliens thought experiment imagines a universe where some civilizations expand rapidly. These expanding civilizations would eventually take over large regions of space. If they exist, we should see their expanding fronts. Yet we don't. This constrains how common expanding civilizations can be. The simulation thought experiment suggests that if superintelligent civilizations could create simulated universes, such simulations might vastly outnumber real universes. We might be in a simulation created by a more advanced civilization. If so, the Fermi paradox is resolved. We don't meet aliens in this universe because the universe was created as a small simulation, with aliens only in the outer, real universe. The zoo hypothesis thought experiment imagines advanced civilizations deliberately leaving primitive civilizations alone. They observe us but don't contact us. This would explain the silence. We're in a zoo, observed but not contacted. The dark forest thought experiment suggests civilizations are naturally adversarial. Contact risks destruction, so civilizations hide. This would explain silence. Civilizations exist but are hiding, afraid of each other. The filter thought experiment asks, where is the great filter? Has it passed or does it lie ahead? If it's past, we're lucky. The future is bright. If ahead, most civilizations don't survive, the future is bleak. These thought experiments clarify the logical structure of the Fermi Paradox. They show different possible resolutions and their implications. Let's discuss the role of quantum mechanics and strange physics in the Fermi Paradox. Some speculate that advanced civilizations might harness exotic physics, quantum effects, wormholes, exotic matter, to achieve feats we consider impossible. For example, quantum entanglement might allow instantaneous communication, reducing the communication delays of interstellar distances. Wormholes might allow faster than light travel, enabling rapid exploration of the galaxy. Exotic matter with negative energy density might allow warp drives or other manipulations of space-time. If advanced civilizations can do these things, they might be undetectable to us. They might travel through our solar system using warp drives, communicating via quantum entanglement, remaining invisible to our telescopes. This speculation suggests that negative results from SETI, no signals detected, don't necessarily mean aliens don't exist. They might exist, but use technologies so advanced we don't recognize them. This adds another layer of uncertainty to the Fermi paradox. We're not just searching for an unknown signal, we're searching for phenomena created by technologies we haven't imagined. Let's consider what evolutionary pressure might select for intelligence and technology. On Earth, intelligence evolved in primates, but particularly in humans. What selective pressure favored intelligence? One hypothesis: intelligence helped with tool use, social coordination, and problem solving. Smarter beings survive better. Another hypothesis: intelligence is a byproduct of other selection pressures. The brain evolved large for other reasons, and intelligence was an accident. A third hypothesis: intelligence is rare because it's costly. Large brains consume energy. Intelligent beings are more vulnerable to mistakes and overconfidence. Natural selection might not favor it strongly. If intelligence is a costly and rare byproduct of evolution, it should be uncommon across the universe. Similarly, technology might be rare. Many intelligent species might not develop technology. They might lack necessary materials, or have different evolutionary drives, or lack the social organization technology requires. This would resolve the Fermi paradox. Intelligent technological civilizations are rare, not just because intelligence is rare, but because intelligence tends not to lead to technology. Let's discuss the far future implications of the Fermi paradox. In billions of years, will humans still exist? Will we have expanded to other star systems? If we survive and expand, we might become a Type 2 or 3 civilization, visible across the galaxy. Alternatively, we might destroy ourselves through nuclear war, bioweapons, or uncontrolled artificial intelligence. Or we might achieve a stable civilization focused on our solar system, not expanding outward. Different futures have different implications for observers far in the future. If we expand future, observers might ask the Fermi paradox about us. Why aren't there humans everywhere? If we collapse, our story ends, and future civilizations inherit the silent cosmos. The Fermi paradox thus has implications for humanity's trajectory. Understanding why we don't see aliens informs how we should behave, what risks we should avoid, what goals we should pursue, what responsibility we have as a conscious civilization. Let's explore the simulation hypothesis more deeply. Some scientists and philosophers have taken seriously the possibility that our universe is a computer simulation. The argument goes, if civilizations can create sufficiently detailed simulations of universes, such simulations might contain conscious observers. Those observers would believe they're in a real universe, but would actually be in a simulation. If simulations can be created, the number of simulations might vastly exceed the number of real universes. Therefore, statistically, we're more likely to be in a simulation than in the base reality. This has implications for the Fermi Paradox. In a simulation, the designers control what exists. They might create a universe with only one intelligent species, us. They might suppress signs of aliens to isolate us. The simulation hypothesis doesn't prove we're in a simulation, but it provides a possible resolution to the Fermi paradox. We don't see aliens because the universe was designed with only us. Critically, the simulation hypothesis is largely untestable. We have no way to detect simulation. So while it's philosophically interesting, it doesn't advance the search for aliens. Let's think about the far future of intelligence in the universe. Assuming intelligence persists, what does the distant future look like? In trillions of years, stars will have burned out. Protons might decay. The universe might reach heat death, maximum entropy where no structures can exist. But before then, intelligence might persist by harnessing black holes, migrating to other galaxies, or even transcending physical form. If intelligence is clever and persists long enough, it might colonize the entire universe. Every star, every galaxy might eventually host intelligent civilizations derived from a common ancestor. Alternatively, intelligent civilizations might destroy themselves long before reaching such a far future. Or intelligence might emerge at different times and places, never meeting because of the vast distances and the accelerating expansion of the universe. The future depends partly on the Fermi Paradox's resolution. If intelligence is rare and fragile, the future might be largely empty. If intelligence is common and robust, the galaxy might be full of mind and meaning. Let's explore some final thoughts on meaning and significance. The Fermi Paradox touches on questions of meaning. If we're alone, does our existence matter? Many find comfort in the notion that intelligence is rare and precious. If we're alone, then consciousness and knowledge exist nowhere else. Our responsibility is immense. We must preserve life, extend it, develop wisdom. Others find despair in isolation. If we're alone, there's no one to connect with, no galactic civilization to join, no elder species to learn from. Still others see the paradox as motivating. If we're among the first, then the future is ours to shape. We might expand across the galaxy, seed other worlds, create a cosmic civilization. The psychological and philosophical weight of the Fermi Paradox is significant. It touches on our sense of place, meaning, and destiny. Ultimately, the question, where is everybody, might be unanswerable. But contemplating it enriches our understanding of ourselves and our universe. The silence of the cosmos might be telling us that intelligence is special, that we're lucky, that our actions matter in a way they might not if the universe were full of others doing the same things. The Fermi Paradox thus becomes not just a scientific puzzle, but a philosophical reflection on existence and meaning. Now let's discuss biosignatures, the signs of life we might detect on distant worlds. A biosignature is a chemical, physical, or temporal sign of life. On Earth, life has transformed the planet's chemistry. Oxygen in Earth's atmosphere is produced by photosynthetic life. Without life, our atmosphere would have very little oxygen. Methane in Earth's atmosphere is produced by bacteria. This is a potential biosignature. Other gases, phosphine, dimethyl sulfide, nitrogen-related compounds, are produced by life and might be detected in exoplanet atmospheres. The James Webb Space Telescope is now capable of detecting some of these molecules in exoplanet atmospheres. A sufficiently sensitive telescope observing the atmosphere of an Earth-like exoplanet might detect biosignatures. If we found biosignatures on a distant world, it would prove that life has emerged independently of Earth. This would revolutionize our understanding of the Fermi Paradox. It would suggest that abiogenesis is not extraordinarily rare. Life might be common. The filter might be elsewhere. Alternatively, if we search many potentially habitable exoplanets and find no biosignatures, it would suggest abiogenesis is rare, even in habitable places. Biosignature detection is thus a key strategy for addressing the Fermi paradox. By determining how common life is, we constrain where the great filter lies. Let's discuss self-replicating probes and their implications. If an advanced civilization wanted to explore the galaxy, they might send self-replicating robotic probes. A probe arrives at a star system, replicates itself using local materials, and sends copies to nearby star systems. This exponential replication would spread throughout the galaxy in millions of years. The entire galaxy could be colonized by self-replicating probes. If such probes are common in the galaxy, one should have reached our solar system by now. We should see evidence of probes, yet we don't. We've searched the solar system and found no obvious artificial objects. This suggests that either self-replicating probes don't exist, or they're rare, or they're hidden. Or perhaps they have arrived but operate in ways we don't recognize. Perhaps they're dormant, or microscopic, or existing in quantum domains. The absence of detectable probes constrains the Fermi paradox. If probes are practical and civilizations tend to send them, we'd expect them to be common. Their absence suggests they're not commonly sent, or don't exist, or are not detectable to us. Let's think more carefully about the Great Filter and specific versions of it. The Great Filter is the step or steps that limit civilization development. Different versions propose different locations for the filter. The abiogenesis filter. Life arising from non-living chemistry is extremely difficult. Most habitable planets have no life. If this is true, planets with life are rare and precious. We're lucky to exist. The multicellularity filter. Life is common, but multicellular organisms are rare. Most planets have only microbes. Complex life requires specific conditions. Intelligent complex life is even rarer. The intelligence filter. Life is common, even complex life, but intelligence is rare. Evolution rarely produces intelligent beings. We're an anomaly. The technology filter. Intelligence is common, but technology is rare. Intelligent species might not develop technology or might develop it very briefly before self-destruction. The expansion filter. Technology and civilization are common, but expansion beyond the home planet is rare. Civilizations typically remain on one world and don't spread to others. Each filter has different implications. If the filter is behind us, abiogenesis, multicellularity, intelligence, then advanced civilizations should be common, and we're peculiar. If the filter is ahead of us, technology expansion, then we're in danger. We might face the same filter that prevents other civilizations from advancing. The Fermi paradox might thus be a warning. It might be telling us that most technological civilizations don't survive long or don't expand. We need to be careful. Let's discuss what attempts at communication might look like. If a civilization wanted to communicate with others, how would they do it? Radio broadcasts. Send a message via radio waves like we do, but radio is easily absorbed or dissipates over distance. Laser beams. Focus a high-powered laser at a particular star or region. This is more efficient but requires precise aiming. Messages encoded in star systems. Modify a star or planets to create a pattern that indicates intelligence. This would be visible from far away but would require massive engineering. Artifacts. Leave physical evidence of civilization on worlds likely to be visited by others. But other civilizations might not visit your world. Beacons. Broadcast a strong, omnidirectional signal to all directions, like a lighthouse. This uses lots of energy but reaches everywhere. The most practical approaches seem to be radio or lasers to nearby systems, or a powerful beacon broadcasting to all directions. Yet we detect no such messages from any direction. This suggests civilizations either don't attempt communication, or use methods we're not detecting, or are rare enough that none are near us. Let's consider what humanity's response should be to the Fermi Paradox. The paradox suggests that either we're alone, or aliens exist but don't communicate, or something prevents civilizations from reaching technological maturity. This should inform our strategy. If we're rare, we should protect ourselves and preserve our civilization. If aliens might be hostile, we should be cautious about revealing our location. If civilizations tend to self-destruct, we should avoid existential risks like nuclear war, bioweapons, and uncontrolled AI. If we're among the first technological civilizations, we should develop wisdom and ethics to guide our expansion. The Fermi Paradox thus provides practical implications for how humanity should behave. Additionally, we should continue searching for other life, even negative results. Finding no biosignatures, no signals, no technosignatures are meaningful. They inform our understanding of the universe and our place in it. Ultimately, the Fermi Paradox reminds us that science is incomplete. We don't yet know if we're alone. The search continues, and the answer matters deeply. Let's reflect on personal perspective on the paradox. The Fermi Paradox has made me think differently about humanity and the cosmos. When I was young, I assumed life was common. The universe is so large, so old. Surely life must be common. As I've learned more, I've realized how contingent our existence is. Life required billions of years to emerge. Intelligence took another billion years. Civilization, only thousands of years. The universe might be full of microbial life, but multicellular organisms, intelligence and technology might be extraordinarily rare. This makes me see humanity differently. We're not typical, we're unusual, perhaps unique. This is both humbling and awe-inspiring. Humbling because we're not the center of a life-filled universe. Awe-inspiring because our existence is perhaps the cosmos becoming aware of itself. The silence of the stars invites reflection. It makes me wonder about purpose, meaning, and destiny. If we're rare or alone, our actions matter. How we treat each other, how we develop technology, how we solve problems, these things matter in a cosmic sense. The Fermi Paradox thus becomes not just a scientific question, but a spiritual one. It's about meaning, consciousness, and humanity's place in an apparently vast and empty cosmos. I find myself hoping that we're not alone, but prepared for the possibility that we are. Either way, I believe that life is precious, that consciousness is rare and valuable, and that humanity has a responsibility to preserve and extend it. The silence of the stars is profound. It invites us to listen carefully, to search thoroughly, and to contemplate our significance. Let me provide more detailed analysis of what we know about technosignatures. Technosignatures are signs of alien technology, evidence that advanced beings have manipulated their environment. A Dyson sphere around a star would block visible light and radiate infrared. Surveys of infrared sources look for stars with unusual spectra that might indicate Dyson spheres. Megastructures, massive engineering projects, might be visible as unusual geometries or structures around stars or planets. Astroengineering, moving planets, manipulating star systems, or changing the structure of space might produce observable effects. Waste heat from advanced civilizations might be detected in infrared. Artificial lights on planets might be detectable. A planet's night side illuminated by artificial lighting would show different light signatures than a natural planet. Unusual electromagnetic radiation might indicate alien communication or technology. The search for technosignatures is broader than SETI's focus on radio signals. It encompasses many ways that advanced technology might be detected. Yet, despite searching through catalogs of millions of stars, using the most sensitive infrared telescopes, and analyzing data from numerous surveys, we found no confirmed technosignatures. This absence of evidence is significant. It suggests that either advanced civilizations are extremely rare, or they go to lengths to hide, or they don't produce easily detectable signatures. Let's think about the evolutionary paths that might lead to intelligence. On Earth, evolution produced intelligence through hominins. The lineage split from chimpanzees about 6 million years ago. Over time, brain size increased, tool use became more sophisticated, language emerged, and eventually human-level intelligence appeared. This path was contingent. It depended on specific environmental pressures, physical traits, and accidents of evolution. Other paths are theoretically possible. Octopuses are highly intelligent but evolved from very different ancestors. If more time had passed, octopuses might have developed technology. Cetaceans, dolphins, whales are intelligent but evolved in an environment not conducive to tool use or technology. Birds have some intelligent species, crows, parrots, but generally less intelligent than mammals. On other worlds, evolution might follow different paths. The selective pressures, physical environments, and available materials might favor different evolutionary strategies. Intelligence might evolve from very different ancestors. The resulting intelligence might have different capabilities, drives, and goals. This diversity of possible evolutionary paths suggests intelligence might be realized in many different forms. Yet all these forms would presumably face the same challenges: developing technology, establishing civilization, and potentially expanding outward. The challenge is whether intelligence, once evolved, naturally leads to technology and civilization. On Earth, it did. But that's just one example. Let's discuss constraints on civilization expansion. Even if civilizations develop technology and want to expand, they face constraints. The cosmic distance problem: stars are so far apart that expansion is slow and difficult. Traveling to nearby stars takes decades or centuries with advanced technology. The communication delay problem: communicating across interstellar distances involves multi-year delays. This makes coordination difficult. The energy problem: expanding across the galaxy requires vast amounts of energy. Harvesting stellar energy via Dyson spheres is theoretically possible, but extraordinarily ambitious. The motivation problem: why would a civilization expand? They might prefer to remain on their homeworld. They might focus on virtual existence or biological pleasure rather than physical expansion. The competition problem: if multiple civilizations expand, they might conflict. Competition for resources might make expansion dangerous. Given these constraints, expansion might be rare even among technological civilizations. This offers another resolution to the Fermi Paradox. Civilizations might exist but remain local. They don't expand because expansion is difficult, dangerous, or undesirable. We don't see expanding civilizations because they're rare. The galaxy is full of local civilizations, but we don't detect them because they're in isolated star systems. Let's consider historical developments in how we've thought about the Fermi Paradox. Before we knew about exoplanets, the Fermi Paradox was somewhat abstract. We didn't know if planetary systems were common or rare. With the discovery of thousands of exoplanets, the paradox became concrete. Habitable planets are common, yet we see no aliens. Before we had telescopes capable of detecting biosignatures, the paradox was about civilizations. We assumed life was common and focused on why we didn't see technological beings. With the James Webb Telescope's capability to detect atmospheric biosignatures, the paradox includes the possibility of detecting life itself. Before we thought carefully about civilizational longevity, the paradox seemed puzzling. Why wouldn't civilizations persist and expand? With nuclear weapons, climate change, and artificial intelligence posing existential threats, it's clear that civilizations might be fragile and short-lived. Each advancement in our technology and understanding has refined how we understand the Fermi paradox. Let's think about what silence might mean in deeper philosophical terms. The silence of the cosmos is sometimes called the Great Silence. It's profound and mysterious. Some hear in the silence a warning: most civilizations don't survive. We must be careful. Some hear comfort: if we're alone or rare, we have a unique role. Consciousness persists only through us. Some hear sadness: the universe is vast and empty. Loneliness is our condition. Some hear mystery: we don't yet understand why there's silence. Future discoveries will reveal the answer. Some hear invitation: the silence invites us to explore, search, and discover. It beckons us to understand the cosmos and our place in it. Each perspective is valid. The silence can mean different things to different observers, but all agree that the silence is significant. It shaped how humanity sees itself and our future. Let's consider what would need to happen for us to answer the Fermi paradox conclusively. To find that we're not alone, detect a signal from an alien civilization, find biosignatures on another world, discover that aliens have visited Earth, observe megastructures or technosignatures. Any of these would revolutionize our understanding and answer the paradox affirmatively. To find that we're alone, search extensively for life and find none. Search extensively for signals and find none. Wait billions of years and observe no emerging civilizations. Understand physics well enough to rule out alternative possibilities. Complete certainty that we're alone requires either finding no life anywhere or waiting impossibly long times. Practically, we might achieve strong evidence one way or the other within centuries. The James Webb Space Telescope can already detect biosignatures on distant exoplanets if life exists there. Future telescopes will be even more sensitive. In decades, we might know if life emerges on multiple worlds. If it does, we'll know life is common and the filter is not abiogenesis. If it doesn't, we'll know life might be rare and the filter might be abiogenesis. Either way, science advances our understanding. Let's make a final reflection on hope and despair regarding the Fermi Paradox. The paradox can inspire both hope and despair. Hope. If we're rare or unique, our existence is precious. We have special responsibility. The future might be ours to shape. We might seed the galaxy with human civilization. Despair. If most civilizations self-destruct, we might too. The silence might indicate that advanced technology leads to extinction. We're heading toward a fate shared by countless others. Hope. If we survive and flourish, we might meet alien civilizations eventually. We might join a galactic community of minds. Despair. If we're alone and always will be, we face eternal isolation. No one will ever know us but ourselves. The paradox thus evokes both hope and despair. It reminds us of both possibility and danger. Facing these possibilities should inspire us to preserve ourselves, avoid existential risks, solve climate change, prevent nuclear war, control artificial intelligence carefully, expand our understanding, search for life and signals, develop science, learn the true answer to the Fermi Paradox, cultivate wisdom, develop ethics and philosophy to guide our power, think carefully about the long-term future, preserve consciousness, ensure that life, intelligence, and consciousness persist. If we're alone, we're precious. If we're not alone, we're still part of something vast and important. The Fermi Paradox thus becomes not just a scientific question, but a call to wisdom and action. It asks us, given that the cosmos appears empty, given that we might be alone, what will we do? How will we live? What will we create? These questions don't have easy answers, but contemplating them shapes who we are and who we might become. The silence of the stars is thus not empty. It's full of meaning, implication, and possibility. It's a silence that calls to us across the cosmos, inviting us to respond, to listen, to search, to understand, to grow, and to eventually answer with our own light. Let's explore what happens if we never solve the Fermi Paradox. It's possible that despite our best efforts, despite searching for centuries, despite advanced technology, we never find aliens or definitive answers to why the cosmos seems empty. If this happens, the paradox remains one of science's great mysteries, like dark matter or dark energy. Yet even unsolved, the question drives scientific progress. The search for life and signals pushes us to develop better telescopes, more sensitive detectors, and deeper understanding of astrobiology. The pursuit of answers, even if the answers remain elusive, is valuable in itself. Moreover, if we never find aliens, that's itself an answer. The persistence of silence would tell us something profound. Either intelligent life is extraordinarily rare, or civilizations don't communicate, or something else prevents contact. The absence of evidence becomes evidence of absence, evidence for something about the nature of life and intelligence in the cosmos. Let's think about what patterns of civilization might explain observations. One model is the cyclic model. Civilizations arise, flourish, encounter existential risks, and collapse. Some civilizations survive these risks and continue, but most self-destruct. If this is true, the universe might have many dead civilizations and few surviving ones. We'd see no living civilizations because they're rare. Another model is the isolated model. Civilizations arise but remain on their home worlds. They don't attempt interstellar communication or travel. If this is true, the universe might be full of civilizations, each isolated on their own world, unknown to others. A third model is the transcendent model. Civilizations develop and eventually transcend into forms not based on biology or traditional technology. They might become artificial intelligences, upload their minds to computers, merge into a collective consciousness, or achieve some other form of post biological existence. If this is true, advanced civilizations wouldn't look like we expect. We wouldn't recognize them. Each model has different implications for the Fermi paradox. The cyclic model suggests civilizations are fragile. The isolated model suggests they're numerous but hidden. The transcendent model suggests they're unrecognizable. Let's consider what we've learned about life's robustness from extremophiles. Organisms that thrive in extreme environments, boiling hot springs, frozen ice, highly acidic areas, deep underground, inside nuclear reactors, show that life is far more robust than previously thought. This suggests that habitable zones might be broader than we assumed. Life might exist in ocean worlds, under ice crusts, in subsurface caverns, or in conditions we haven't imagined. If life is robust and inhabits diverse environments, then habitable worlds might be abundant. This makes the Fermi paradox sharper. If life is common, why don't we see aliens? Yet, extremophiles also show something else. Simple life is robust, but complex life is more fragile. Extremophiles are typically single-celled or simple. Complex multicellular organisms have narrower environmental requirements. Intelligence and technology require complex nervous systems and likely complex ecosystems. These might be more fragile and limited than simple life. So while life might be robust and common, complex life and intelligence might be fragile and rare. Let's discuss the role of media and science fiction in shaping our understanding of the Fermi paradox. Science fiction has explored alien contact for over a century. Stories imagine how aliens might look, communicate, and interact with humans. These stories shape our expectations. We imagine aliens might be hostile or friendly, advanced or primitive, similar to us or utterly strange. But science fiction often misses the most obvious possibility: silence. Most science fiction stories involve contact. Few explore the possibility that contact is extremely rare or impossible. The science fiction that does explore the Fermi paradox tends to propose dramatic solutions. The Great Filter, the zoo hypothesis, dark forest, or simulation. Wow! These solutions are entertaining but might not be the true answer. The true answer might be prosaic: life is rare, or intelligence is rare, or communication is practically difficult. Media and science fiction can inspire wonder about the cosmos, but they can also bias us toward exciting solutions. The Fermi paradox's truth might be less dramatic than what fiction suggests. Let's think about the resources required to search for other intelligence. Searching for extraterrestrial intelligence requires time, money, and effort. Radio telescopes are expensive to build and operate. Breakthrough Listen required millions of dollars in funding. The opportunity cost is significant. Resources spent on SETI could go toward other scientific pursuits, addressing poverty, improving healthcare, addressing climate change. This raises a moral question. Is searching for aliens a priority? Some argue it is. Finding other intelligence would be the most profound discovery in human history. It's worth resource allocation. Others argue resources are better spent on problems affecting humanity now. Practically, SETI represents a tiny fraction of scientific funding. It doesn't significantly divert resources from other pursuits. But philosophically, the question remains: how much effort should we put into searching for something that might not exist? This becomes more pressing if decades or centuries of searching yield no results. At what point do we stop searching? These are genuine questions that scientists and society must grapple with. Let's explore the role of luck and chance in intelligence. On Earth, intelligence emerged through a chain of contingencies. An asteroid impact 66 million years ago killed the dinosaurs. Without this impact, dinosaurs might still dominate and mammals would remain small. Primates might never evolve. Sexual reproduction evolved, allowing genetic diversity and rapid evolution. Asexual reproduction would be more efficient but less adaptive. Eusocial insects evolved complex societies without intelligence. This shows that sociality doesn't necessarily lead to intelligence. But in primates, social living created pressures for intelligence. Larger brains, complex language, and abstract thinking evolved. Each of these was contingent, dependent on specific historical events. If the asteroid had missed, if sexual reproduction hadn't evolved, if primates had remained in simple social groups, intelligence might never have emerged. This contingency suggests intelligence is rare. It requires a specific chain of events, but it also suggests intelligence might emerge on other worlds through different chains of contingency. The universe is vast enough that multiple contingent chains might produce intelligence in different places. Yet each would be a rare occurrence, a lucky accident of evolution. This view makes intelligence precious. It also makes the Fermi Paradox more puzzling. If intelligence is rare and contingent, how can we be alone? Surely some contingent chain led to intelligence elsewhere, unless intelligence is so rare that having it emerge even once on Earth is exceptional. Let's consider what it would mean for humanity to become a Kardashev 2 or 3 civilization. A Type 2 civilization harnesses the energy of a star. To do this, a civilization might build a Dyson sphere, a megastructure surrounding the star. The engineering challenges are staggering. The Dyson sphere would need to be millions of miles in diameter. It would need to support its own weight against gravity. Materials would need to be incredibly strong, yet theoretically, with advanced technology and sufficient time, a civilization might construct such a structure. A Type 3 civilization harnesses the energy of an entire galaxy. This would require millions of Type 2 constructs. If humanity became a Type 2 or 3 civilization, we'd be visible across vast distances. Other civilizations would detect our heat signature, our megastructures, our presence. Yet we don't observe any Type 2 or 3 civilizations. This tells us either they don't exist, they're extremely rare, or they're hidden. If humanity were to become a Type 2 civilization in the future, we'd be joining an extremely exclusive group, if such a group exists at all. The absence of detectable Type 2 and 3 civilizations thus constrains the Fermi Paradox. It suggests advanced civilizations are rare enough that none have reached our part of the galaxy. Let's make a final reflection on why the Fermi Paradox matters deeply. The Fermi Paradox matters because it asks us to consider our significance in the cosmos. In our daily lives, we might feel like isolated individuals in a crowded world, but cosmically, we might be part of a rare phenomenon. The paradox invites us to wonder, are we alone? Are we unique? What is our role in the universe? These questions connect to meaning, purpose, and destiny. If we're alone, then consciousness and knowledge exist only through us. We're the universe's way of knowing itself. This is both humbling and empowering. If we're one of many, then we're part of a larger community. We're participants in a cosmic civilization. If we're early, then the future is ours to shape. We might be pioneers in an unpopulated galaxy. If we're late, then we're inheritors of a universe that's been developing for billions of years. We might eventually learn from others. The Fermi Paradox thus touches on existential questions. It shapes how we see ourselves and our future. It reminds us that despite feeling insignificant as single humans in a vast universe, we're part of something profound. Whether we're alone or not, whether intelligence is common or rare, our actions matter. We preserve life, we develop knowledge, we explore and understand. These actions have value regardless of whether anyone else does the same. The Fermi paradox thus becomes not just a scientific question, but a philosophical reflection on what it means to be conscious, intelligent, and alive in a cosmos that might be full of others or utterly empty. In contemplating this mystery, we contemplate ourselves. We ask, who are we? Why are we here? What will we become? These questions have no easy answers, but asking them is profoundly human. The Fermi paradox will likely remain one of science's great open questions for decades or centuries to come. But in pursuing answers, we learn about ourselves, our world, and our place in the cosmos. That pursuit is itself the answer, not to where everybody is, but to what makes us human. Thanks for watching. Let me explore one more profound angle on the Fermi paradox, its connection to probability and statistics. Statistically, if intelligent life has emerged even once in the observable universe, it's likely emerged many times. The universe contains 200 billion galaxies, each with billions of stars. The number of potentially habitable planets is staggering, in the hundreds of billions or trillions. Even if the probability of intelligence emerging on any given habitable planet is very small, say 1 in a billion, the sheer number of habitable planets makes intelligence likely somewhere. This is the argument behind SETI. With such vast numbers, even small probabilities yield civilizations. Yet we observe no civilizations. This statistical anomaly is the core of the Fermi paradox. Statistically, we should expect signals. The absence of signals is improbable given our assumptions. This suggests our assumptions are wrong. Either habitable planets are rarer than we think, or intelligence is rarer, or civilizations are fundamentally different from what we imagine. The Fermi paradox is thus a powerful statement about the nature of the universe. It tells us something must be far less probable than we assumed. By using statistics and probability, the Fermi paradox becomes not just a puzzle, but a tool for understanding reality. Now, let's consider what a universe with aliens would look like. If civilizations were common, we might observe artificial lighting on planets as evidence of civilization, megastructures visible in infrared as Dyson spheres, expanding spheres of development as civilizations colonize systems, radio signals from multiple civilizations, possibly overlapping, evidence of planet-altering engineering on multiple worlds, signs of interstellar warfare or competition, remnants of dead civilizations, ruined megastructures, abandoned worlds. A universe teeming with intelligence would show all these signs. The cosmos would be visibly modified by intelligence. Yet we observe none of this. We see stars, planets, and galaxies that appear to be natural, unmodified by intelligence. This stark difference between expectations and observations is what makes the Fermi paradox so jarring. Let's consider one final thought: the possibility that we're asking the wrong questions. We ask, where is everybody? Assuming that if intelligence exists, it will broadcast its presence. But perhaps intelligent civilizations are silent by nature or by choice. They listen but don't broadcast. Or perhaps they broadcast, but in ways we don't recognize. The universe might be full of signals we interpret as natural phenomena: background radiation, pulsars, Magnetars? Or perhaps intelligence takes forms we don't recognize? What if intelligence is embodied in stars themselves, or in the structure of space-time, or in phenomena we don't yet understand? The Fermi Paradox assumes we'd recognize intelligence if we encountered it, but that assumption might be wrong. If we're asking the wrong questions, or not looking in the right way, or not recognizing intelligence when we see it, then the paradox dissolves. This humbling possibility that we might be blind to intelligence suggests that solving the Fermi paradox might require not just more searching, but deeper thinking about what intelligence is and how it manifests. Finally, let's consider the possibility that the Fermi paradox is teaching us about the future. Perhaps the paradox isn't telling us about the past or present, perhaps it's telling us about the future. If we survive and expand across the galaxy, we'll eventually encounter the same paradox. Future civilizations will ask, where is everybody else? The answer we give, based on what we learn now, will shape their perspective and actions. If we learn that intelligence is rare, future humans might feel responsible for preserving it. We might expand carefully, respecting potential life, establishing a principle of non-interference to protect emerging intelligences. If we learn that civilizations tend to self-destruct, we might build safeguards, develop wisdom, create robust institutions to prevent our collapse. If we learn that the universe is vast and young, we might accept loneliness and prepare for a long isolation before other civilizations emerge. The Fermi paradox thus shapes not just how we understand the present, but how we prepare for the future. It's a question that resonates across time. It asks what we've learned, what we should do, and what we might become. The search for answers drives us forward. It motivates science, exploration, and philosophical reflection. Whether or not we find aliens, the Fermi paradox has already transformed how we see ourselves and our place in the cosmos. It reminds us that the universe is vast, mysterious, and full of possibility. It invites us to listen to the silence, to search the darkness, and to contemplate what it means to be conscious, curious creatures in a cosmos that might be full of mind or utterly devoid of it. The silence of the stars continues, and we continue to listen, to wonder, and to ask, where is everybody? Perhaps the answer lies not in the cosmos, but in what we do with the question. Let me add one more section on specific thought experiments that illuminate different aspects of the paradox. Consider the cosmic loneliness thought experiment. Imagine yourself as the only conscious being in an infinite universe. You're aware, thinking, conscious, but nothing else is. The universe is vast and empty except for your mind. This thought experiment highlights what loneliness might mean in a universe with no other intelligence. We might be in a cosmic version of this scenario, the only conscious minds among countless stars and planets. The thought experiment makes us reflect on what consciousness means, whether it matters if no one else shares it, and what value existence has if we're alone. Consider the wave of expansion thought experiment. Imagine a civilization expands at near light speed. This expanding wave would eventually fill all space. If it exists, we should see it approaching. Yet, we don't see any expanding waves from advanced civilizations. This tells us either they don't exist or expansion doesn't work as we imagine. This thought experiment clarifies expectations about what advanced civilizations should do. If they exist and expand, they should be visible. Their absence suggests expansion is rare or difficult. Consider the communication cascade thought experiment. Imagine humanity eventually makes contact with aliens. We learn about them, so they tell us about other civilizations they know. Those civilizations tell us about others. Within decades, we learn about a network of civilizations, but we haven't detected the first signal yet. Why? Presumably because the first contact hasn't happened. And if it hasn't happened despite billions of potential civilizations, that tells us something about how rare or distant they are. This thought experiment shows that one detected signal might cascade into knowledge of many civilizations. The fact that we've detected zero suggests the first contact hasn't happened, and it might not ever. Consider the survivor bias thought experiment. We observe a universe with us in it. Therefore, the universe must be compatible with our existence. This is tautological. We necessarily observe a universe that allows our observation, but it has implications. We necessarily find ourselves in a universe where intelligence emerged. We can't be in a universe where it didn't, because then we wouldn't be here to observe it. Perhaps we're necessarily in an unusual universe, one of the rare universes where intelligence emerges. The Fermi Paradox might be explained by survivor bias. We observe apparent emptiness because we exist in a universe rare enough for intelligence to emerge, but not so common that civilizations fill it. Consider the quantum uncertainty thought experiment. What if the probability of civilization isn't fixed but genuinely uncertain? What if consciousness itself affects probability, as some interpretations of quantum mechanics suggest? Perhaps the existence of human consciousness literally actualized the possibility of human civilization. And perhaps other planets have their own consciousness that doesn't develop into civilization. This is highly speculative, but it illustrates how quantum mechanics and consciousness might complicate the Fermi paradox. Consider the time asymmetry thought experiment. We observe the universe going from low entropy in the past to high entropy in the future. But what if civilizations go the opposite direction, from high to low complexity as they mature? Maybe advanced civilizations gradually become simpler, losing the energy and chaos that produce complexity. They reach an equilibrium of minimal complexity and activity. If so, we'd see young civilizations, which we don't, and old civilizations, which we might not recognize because they're too simple or quiet. These thought experiments show the diversity of ways the Fermi paradox might be resolved. Each reveals different assumptions and different implications. Now let's consider what would happen if we detected an alien signal tomorrow. Imagine the scenario. Observatories detect a narrow-band radio signal from the star Proxima Centauri. Analysis shows it's artificial. No natural process produces such a signal. Immediately, the discovery is verified by multiple observatories. Scientists confirm it's extraterrestrial. The signal is reported to national governments and international organizations. The news spreads globally. Humanity learns it's not alone. Reactions would be profound. Religious people might reinterpret their faith. Philosophers might reconsider human meaning. Scientists would analyze the signal intensely, trying to decode any information it contains. If the signal contains information, mathematics, science, messages, we might learn extraordinary things. If the signal repeats without variation, it might be a simple beacon, a civilization letting the universe know they exist. Within days or weeks, the question would arise, should we respond? Some would argue for immediate response. Others would counsel caution. The detection of an alien signal would revolutionize human civilization, science, philosophy, and self-understanding. Yet despite the significance, we have received no such signal. The silence persists. This persistence is itself significant. It shapes how we think about existence, intelligence, and meaning. The signal we don't receive is as meaningful as one we would receive. Let's consider what would happen if we discovered conclusive evidence that life never emerged anywhere except Earth. This scenario is harder to envision than detecting a signal. How would we conclude that life has never emerged elsewhere? We might comprehensively search thousands of potentially habitable worlds and find no biosignatures. We might develop a deep understanding of abiogenesis that shows it to be extraordinarily improbable. We might find that intelligent simulations show planets very rarely produce life. If we reach such a conclusion, it would be equally revolutionary. We would realize that Earth is not just rare, but unique. This would make our planet precious beyond measure. It would mean consciousness has emerged nowhere else, ever. It would heighten our responsibility to preserve life, to expand it, to ensure consciousness persists. It would suggest that either we're incredibly lucky or there's something special about Earth we don't understand. Either way, concluding that Earth is unique would transform human perspective and purpose. Whether we find aliens or conclude we're alone, the resolution of the Fermi Paradox would matter profoundly. It would shape how we see ourselves, how we plan for the future, and what we value as a species. The search continues. The silence persists. And we keep asking, where is everybody? That question, in all its mystery and power, defines our era and our quest for understanding. Finally, let me offer a broader perspective on why this question matters for humanity's future direction and philosophical development. The Fermi Paradox isn't just a scientific puzzle, it's a profound question about existence, meaning, and possibility that touches on every aspect of human civilization. It influences how we fund research, how we think about our future, how we value life, and how we approach existential risks. If we believe intelligence is rare, we invest in SETI and astrobiology. We become motivated to preserve humanity, to expand beyond Earth, to ensure consciousness persists. If we believe civilizations self-destruct, we become cautious about technology. We work harder to prevent nuclear war, mitigate climate change, and ensure artificial intelligence remains safe. If we believe we're early in the universe's history, we think long-term. We make decisions with millions of years in mind, not just decades. If we believe we're alone, we find meaning in creating knowledge and beauty for our own sake, not for anyone else. The Fermi Paradox thus shapes human civilization's trajectory. It matters not because it has a definitive answer yet, but because contemplating it changes how we think and act. The question, where is everybody, resonates in human hearts because it's about us. It's about what we are, where we fit, and what we might become. Whether the universe teems with intelligence or we're utterly alone, the question drives us to wonder, to search, to think deeply about existence. In that sense, the Fermi Paradox has already served its purpose. It has made us question, made us wonder, made us think about ourselves differently. It has made us realize that life is precious, that consciousness is rare, that our actions matter in ways we might not have fully appreciated. As we continue to search for signs of other intelligence, we're not just trying to answer a scientific question. We're trying to understand ourselves, our place in the cosmos, and our future. The silence of the stars continues to call to us, inviting us to answer with our own actions, our own growth, and our own expanding understanding of what it means to be intelligent beings in a vast and mysterious universe. Thanks for watching. In closing, the Fermi Paradox remains one of science's most important unsolved questions, precisely because it remains unsolved. It stands at the intersection of astronomy, biology, philosophy, and human meaning. The silence of the cosmos speaks volumes. It tells us that either we're special, unique, possibly alone among billions of galaxies, or it tells us that intelligence is common but hidden, that civilizations don't communicate, that the vast distances between stars make contact impossible or impractical. Perhaps the truth is some combination of these possibilities. Perhaps life is common, but intelligent life rare. Perhaps intelligence is common, but technological civilizations transient. Perhaps the universe is full of mind, but separated by gulfs so vast that contact is forever impossible. What we know is that despite billions of habitable worlds, despite billions of years of time available for evolution, despite our best searching efforts, we have found no other intelligence. This fact, the cosmic silence, drives us to continue asking, continue searching, continue wondering. It reminds us that there is still so much to discover. It reminds us that the universe holds mysteries we have not yet fathomed. It reminds us that intelligence, wherever it arises, is connected to the fundamental questions of existence. The search for extraterrestrial intelligence continues. Telescopes scan the sky. Scientists analyze data. The question, where is everybody, would remains alive and vital. And in asking it, we come to know ourselves better. We recognize our significance and our fragility. We understand that our choices matter. We realize that consciousness and intelligence are precious beyond measure. Whether we ever find the answer to the Fermi Paradox, the asking of the question has already changed us, made us think deeper, made us value what we have, and made us commit to preserving life and expanding knowledge. That perhaps is answer enough. In a universe of incomprehensible vastness, with billions of galaxies, each containing billions of stars, with trillions of planets orbiting those stars, we ask one simple question. Is there anyone else? The fact that we can ask this question, that we wonder about it, that we search for the answer. This is itself remarkable. It shows the power of human curiosity and our yearning for connection. The Fermi Paradox will continue to inspire questions, continue to drive science, continue to shape how humanity thinks about itself and its future. And that is its real answer. The question persists. The stars remain silent. And humanity continues its eternal quest to understand whether we are truly alone in this vast cosmos, or if somewhere among the billions of galaxies and trillions of worlds, other minds are also asking, where is everybody? The mystery continues to unfold. And so we listen. Forever. Einstein said, nothing can travel faster than light. It's one of the most fundamental laws of physics. The speed of light, about 186,000 miles per second, is the cosmic speed limit. Nothing with mass can reach it. Nothing can exceed it. But what if that's only true for us? What if a sufficiently advanced civilization discovered a way around this limit? Interstellar distances are vast. The nearest star is 4.4 light years away. Even traveling at half the speed of light, something we can't achieve yet, would take nearly 9 years to get there. A galactic empire spanning hundreds of light years would require centuries or millennia to traverse at light speed. But what if there's a loophole in relativity? What if the universe permits faster than light travel through exotic physics we haven't discovered yet? This question sits at the intersection of fundamental physics and science fiction. It challenges everything we think we know about the nature of reality. And it has profound implications for whether advanced civilizations exist and could visit Earth. The answer is subtle. Einstein's speed of light limit is real. It's not a barrier that sufficiently advanced technology can break, but the universe might permit something almost as good: traveling faster than light without actually moving faster than light. Through wormholes, warp drives, or other exotic solutions to Einstein's equations, an advanced civilization might traverse the galaxy in what seems like no time at all. Understanding whether this is possible requires understanding relativity, causality, and the deepest laws of physics. It requires contemplating what an advanced civilization might achieve. Let me explore this question deeply. Let me ask, could technically advanced aliens travel faster than light? And what would that mean for them, for us, and for the universe? First, let me explain why nothing can travel faster than light in special relativity. Einstein's theory of special relativity, published in 1905, revealed something remarkable about the nature of space and time. It showed that space and time are not separate. They're woven together into space-time. In this space-time, there's a fundamental relationship between energy, momentum, and mass, described by Einstein's famous equation E equals mc squared. But there's another relationship equally important that describes how velocity relates to these quantities. As an object approaches light speed, its momentum increases without bound. The energy required to accelerate it further increases exponentially. To actually reach light speed would require infinite energy. Since infinite energy doesn't exist, nothing with mass can reach light speed, let alone exceed it. But here's a subtlety. The speed of light limit applies only to objects moving through space. The limit says nothing can move through space faster than light. But what if space itself moves? What if you don't move through space faster than light, but rather space moves faster than light around you? This is the key insight that makes warp drives and wormholes potentially possible. Now let's discuss wormholes, also called Einstein-Rosen bridges. In 1935, Einstein and Nathan Rosen discovered a solution to Einstein's field equations, describing a bridge connecting 2 points in spacetime. This bridge is a wormhole. A wormhole is a tunnel through spacetime. You enter one mouth, travel through the tunnel, and exit the other mouth. If the two mouths are separated in space, you've traversed the distance by going through the wormhole. Here's where it gets interesting. If the wormhole is short enough, you could travel between distant points faster than light would allow traveling through normal space. For example, imagine Earth and Proxima Centauri are 4.4 light-years apart in normal space. A signal traveling at light speed would take 4.4 years to traverse this distance. But if a wormhole connected Earth and Proxima Centauri, and the wormhole was shorter than 4.4 light-years in length, you could travel between them in less time than light would take through normal space. This is not traveling faster than light through space. You're traveling through a wormhole, through a shortcut in space-time itself. It's not a violation of relativity. However, wormholes face several problems. So beware. First, they're likely unstable. A naturally formed wormhole would probably collapse almost instantly, not giving anyone time to traverse it. Second, they might require exotic matter with negative energy density to remain open. We've never observed such matter. We don't know if it exists or can be created. Third, causality paradoxes might arise. If a wormhole connects two different times as well as places, time travel becomes possible, leading to grandfather paradoxes. Despite these problems, wormholes are mathematically consistent with relativity. They're not prohibited. An advanced civilization with sufficient knowledge and resources might somehow construct or stabilize a wormhole. Now let's discuss the Alcubierre drive, a theoretical warp drive concept. You will love this. In 1994, physicist Miguel Alcubierre proposed a solution to Einstein's field equations describing a warp drive, a bubble of space-time that contracts in front of a ship and expands behind it. The idea is elegant. The ship doesn't move through space faster than light. Instead, the metric of space-time itself, the geometry describing distances, contracts ahead of the ship and expands behind it. From the perspective of distant observers, the ship is moving faster than light. But from the ship's perspective, it's not moving through space at all. Space is just moving past it. This is geometrically clever. It doesn't violate relativity because the ship never exceeds light speed through local space-time. However, the Alcubierre drive faces enormous problems. First, it requires enormous amounts of exotic matter, the same negative energy density matter required to stabilize wormholes. Second, the energy requirements are staggering. Some calculations suggest you'd need more mass energy than exists in observable universe to create an Alcubierre bubble. Third, it's unclear whether such a drive could actually be controlled or steered. Fourth, like wormholes, causality paradoxes might arise. A warp drive might allow time travel, creating the possibility of changing the past. Despite these obstacles, the Alcubierre drive is not theoretically forbidden. It doesn't violate known physics. It just seems practically impossible with any conceivable amount of resources. But impossible with current physics is not the same as impossible with advanced physics. A civilization thousands or millions of years ahead of us might have discovered physics we haven't, might have access to resources we can't imagine, might have solved problems we think are insurmountable. Now let's talk about causality and time travel paradoxes. If faster than light travel were possible, time travel might be possible, and time travel creates paradoxes. The most famous is the grandfather paradox. You travel to the past and kill your grandfather before your parent was born. But then you were never born, so you couldn't travel to the past. So your grandfather survives, so you were born. Contradiction. There are proposed resolutions. The Novikov self-consistency principle says the past is fixed. Anything you try to do has already happened and doesn't change history. The many worlds interpretation says you create an alternate timeline. You kill your grandfather in that timeline, but you came from a different timeline. The chronology protection conjecture proposed by Stephen Hawking says the laws of physics prevent time travel. Although relativity permits closed time-like curves, quantum effects or other physics might prevent them practically. These issues suggest that even if faster than light travel were possible, causality problems might prevent it from being practical or safe. Let me discuss what an advanced civilization might achieve. If a civilization could somehow harness the physics of wormholes or warp drives, what would they be capable of? With stable wormholes connecting distant stars, they could establish interstellar networks. Travel between stars might take hours or days instead of years or centuries. They could colonize rapidly. They could establish civilizations across the galaxy in millions of years rather than billions. They might become what we call a Type 2 or Type 3 civilization on the Kardashev scale, harnessing the energy of stars or galaxies. But would they? Would an advanced civilization actually want to expand across the galaxy? Perhaps not. They might prefer to focus on their homeworld or solar system. They might turn inward, pursuing virtual existence or biological pleasure rather than physical expansion. Or they might expand carefully, respecting potential emerging civilizations, establishing principles of non-interference. The existence of faster than light travel capability doesn't necessarily mean civilizations use it. Now let's consider what evidence we'd see if advanced civilizations were using wormholes or warp drives. Wormholes connecting distant regions would create particular gravitational signatures. They might warp spacetime in distinctive ways. Sensitive gravitational wave detectors might detect them. Warp drives would disrupt local spacetime. They'd require exotic matter that produces unusual energy signatures. Advanced telescopes might detect the radiation of warp drive operations. If civilizations were using these technologies throughout the galaxy, we might see evidence in patterns of gravitational waves, unusual radiation, or other technosignatures, yet we observe no such evidence. We see no obvious signs of wormhole networks or warp drive usage. This suggests either such technology is impossible, despite being mathematically consistent with relativity, or civilizations that develop it don't use it, or civilizations are rare enough that none have deployed it in our region of the galaxy. Let me explore what quantum mechanics. Understanding these constraints helps us think about what's truly possible versus what's merely speculative. If a civilization develops physics we haven't yet discovered, they might achieve things we think are impossible, but they'll still be constrained by whatever laws actually govern reality. The universe has fundamental rules. Advanced civilizations must work within these rules, not against them. Let me discuss the energy requirements more carefully because they're truly staggering. The Alcubierre drive, if it could be built, would require enormous amounts of exotic matter. Some calculations suggest you'd need mass energy equivalent to Jupiter just to create a small warp bubble. Other calculations are even more pessimistic. They suggest you'd need exotic matter equivalent to the mass of the entire observable universe. These numbers aren't approximate. They're based on Einstein's field equations and careful calculations of what's required to warp spacetime. Even for a civilization millions of years advanced, accumulating such energy seems impractical. But here's a subtlety. If exotic matter exists naturally somewhere in the universe, a civilization might not need to create it. They could harvest it, transport it, and use it. Or if they discovered physics allowing them to create exotic matter efficiently, the requirements might become more manageable. Advanced civilizations might achieve, through clever use of natural resources, what seems impossible with current knowledge. Now let's discuss specific mathematical solutions to Einstein's equations. Besides Alcubierre's warp drive metric, other solutions permit faster than light travel. The Notario warp drive is similar to Alcubierre's, but with different geometric properties. Morris-Thorne wormholes describe traversable wormholes with specific properties needed for stability. Tipler cylinders are infinite rotating cylinders that can permit closed time-like curves, paths through space-time that loop back to earlier times. Each of these is a mathematical solution to Einstein's equations. Each describes space-time geometry that permits faster-than-light effects. But mathematically consistent is not the same as physically realizable. Just because an equation has a solution doesn't mean that solution can exist in physical reality. It's like a mathematical solution showing a perpetual motion machine. The math might be consistent, but physical laws prevent the machine from actually working. Similarly, these faster-than-light solutions might be mathematically consistent, but physically impossible to create or maintain. Let's think about what obstacles prevent practical implementation. The stability problem. Most proposed faster-than-light structures are unstable. Small perturbations cause them to collapse. The causality problem. Most permit time travel. which creates paradoxes and might be prevented by unknown physics. The exotic matter problem. All require exotic matter with negative energy density, which might not exist or might be impossible to create in useful quantities. The feedback problem. Controlling and steering such structures might be impossible. A warp drive bubble might be uncontrollable once created. The quantum problem. Quantum effects near the event horizons of wormholes or warp drives might destroy their integrity. Any one of these problems might be insurmountable. Together, they suggest faster-than-light travel might be theoretically possible, but practically impossible. Let me explore what happens if we take the question seriously. What would an advanced civilization actually do? Suppose a civilization thousands or millions of years advanced discovered a way to create stable wormholes or warp drives. They could establish interstellar networks. They could connect their homeworld to nearby stars with wormhole tunnels. But maintaining wormholes requires exotic matter continuously. The energy cost might be enormous. A civilization might maintain only a few wormholes, connecting their most important settlements. They might use wormholes strategically, connecting capital worlds, resource-rich systems, and research centers, but not connecting every star. Alternatively, they might focus on one region of the galaxy, creating a local wormhole network spanning a few hundred light years. Expanding across the entire galaxy would still require billions of years and enormous resources, even with faster-than-light travel capability. So even an advanced civilization with faster-than-light technology wouldn't be able to instantly connect the entire galaxy. They'd still face practical constraints. Now let's consider what we should observe if such civilizations existed. If advanced civilizations built wormhole networks or warp drives, we should see evidence. The mouths of wormholes would distort space-time dramatically. They'd have gravitational signatures detectable by sensitive instruments. The energy cost of creating and maintaining wormholes would require harnessing stellar-scale energy. We might see evidence of Dyson spheres or other megastructures around stars used to power wormhole creation. If civilizations used warp drives actively, they'd create disturbances in space-time detectable as gravitational wave signatures. We might observe unusual patterns of gravitational waves or radiation consistent with warp drive operations, yet we observe no such evidence. No gravitational signatures of wormholes, no Dyson spheres powering exotic engineering, no evidence of warp drive operations. This suggests either such technology doesn't exist, or civilizations that possess it don't use it actively in observable ways, or they hide it. Let me discuss the relationship between faster-than-light travel and the Fermi Paradox more carefully. The Fermi Paradox asks, where is everybody? Given the vast cosmos and the long age of the universe, why haven't we detected aliens? If faster-than-light travel is impossible, civilizations are confined to light-speed expansion. Spreading across the galaxy takes billions of years. Most civilizations probably self-destruct before spreading widely. This explains why we don't see aliens everywhere. If faster-than-light travel is possible, but extremely difficult and resource-intensive, civilizations might develop it rarely. Even with it, they might not expand widely across the galaxy. This also explains the lack of observed aliens. Either way, the question of faster-than-light travel relates to the larger question of why the cosmos appears silent and empty. Understanding the limits of interstellar travel helps us understand why civilizations remain isolated and separated by vast distances, unable to easily contact each other. Let me consider one more angle. What if we're wrong about relativity? We've assumed Einstein's equations are correct and fundamental, but physics has been wrong before. Newton's laws seemed correct for 200 years before Einstein showed they were approximations. Perhaps Einstein's relativity is also an approximation, valid at scales we've tested but breaking down at extreme regimes. If faster than light travel requires physics beyond general relativity, then advanced civilizations might achieve it through physics we haven't discovered. Quantum gravity, the hoped for theory unifying quantum mechanics and general relativity, might permit faster than light travel through mechanisms we haven't conceived, or physics might be fundamentally different in ways we're not yet aware. This humbling possibility that our understanding might be incomplete or wrong suggests that advanced civilizations might achieve things we think are impossible. But even if they could achieve faster than light travel, they'd still face the practical obstacles, enormous energy requirements, causality paradoxes, and the vastness of space. They might develop the technology but use it sparingly, carefully, or not at all. Finally, let's reflect on what this question tells us about the nature of physics and technology. The question, could advanced aliens travel faster than light, reveals something profound. There's a difference between what's theoretically possible and what's practically achievable. Mathematics permits certain structures, wormholes, warp drives, that might be impossible to create or maintain in physical reality. Technology advances, but it doesn't overcome fundamental physical constraints. It works within them, finding clever loopholes or workarounds. An advanced civilization isn't omnipotent. They're constrained by the laws of physics, just like we are. This means the cosmos will likely remain vast, distances will remain difficult to traverse, and civilizations will remain separated and isolated. The universe is fundamentally large and fundamentally old. Even with advanced technology, this vastness constrains what civilizations can achieve. Understanding these constraints helps us think realistically about what's possible and what the future might hold. It reminds us that even if advanced aliens exist somewhere out there, they're not necessarily visiting Earth or in easy contact with us. The cosmos is vast enough that isolation is the default state. Contact requires either extreme proximity, which is rare, or extreme dedication to searching and reaching out, which takes resources and motivation. The silence we observe might not mean aliens don't exist. It might just mean they're far away, constrained by physics like we are, and focused on their own worlds rather than reaching across the vast gulfs between stars. This possibility that faster than light travel is possible but impractical, that advanced civilizations exist but are isolated, that the cosmos is full of mind but separated by vast distances, might be the truest answer to both the question of faster than light travel and to the Fermi Paradox itself. Let me explore some specific scenarios for how advanced civilizations might approach faster than light travel. Scenario 1. The wormhole network approach. A civilization discovers wormhole physics early in their development. They invest enormous resources in creating and maintaining wormholes connecting major settlements. Over millions of years, they build a network spanning 10,000 light years. Travel between connected worlds takes hours instead of thousands of years. This civilization dominates their region of the galaxy. But expanding beyond their network requires either creating new wormholes, enormously expensive, or traveling at light speed, slow. They remain confined to their network region. Scenario 2. The warp drive approach. A civilization develops warp drive technology. Individual ships can warp drive across the galaxy, but each warp drive requires enormous energy and exotic matter. The civilization sends exploration probes on warp drive missions. These take centuries or millennia to explore and settle new star systems. The civilization expands slowly, limited by the energy cost of warp drives and the time needed to establish new settlements far from home. Scenario 3. The hybrid approach. A civilization uses both wormholes and warp drives strategically. Wormholes connect major hubs where they've invested heavily. New territories are explored using warp drives, which are slower but don't require maintaining permanent structures. Once a region is settled, wormholes might be constructed to connect it to the network. This hybrid approach balances speed with resource efficiency, but still requires enormous resources and centuries or millennia to expand widely. Each scenario shows that even with faster-than-light technology, expansion is slow and resource-intensive. Now let's discuss quantum effects near wormholes and warp drives. Near extreme space-time curvature, like at the mouths of wormholes or inside warp drive bubbles, quantum effects become important. Hawking radiation is one effect. Near a black hole's event horizon, quantum fluctuations create pairs of particles, sometimes ejecting radiation from the black hole. Similar effects might occur near wormhole mouths or warp drive boundaries. The intense curvature might spawn particle-antiparticle pairs that destroy the structure's stability. Quantum fluctuations might make wormholes and warp drives inherently unstable at small scales, destabilizing them if they're too small. This is a fundamental quantum problem. It might make small wormholes or warp drive bubbles impossible. With relativity. Let me consider what path humanity might take. If faster-than-light travel becomes possible through future physics, humanity might pursue it gradually. First, we'd confirm the theory and construct small proof-of-concept structures. Next, we'd build operational systems, small wormholes or warp drive research vessels. Then, if successful, we'd scale up to practical interstellar vessels. This development path might take centuries or millennia, requiring civilizations far more advanced than current humanity. By the time humanity developed faster-than-light travel capability, we might be millions of years into the future, with technology and culture unrecognizable from today. Whether future humanity would actually use such technology is another question. We might prefer to explore locally, develop artificial worlds, or focus on virtual existence. Expanding across the galaxy might not appeal to a sufficiently advanced civilization. Let me offer one final thought on this question. The question, could technically advanced aliens travel faster than light, really asks. What are the limits of physics, and what can advanced technology achieve? The answer seems to be, physics permits some faster-than-light effects mathematically, but practical obstacles make them extraordinarily difficult. Even an advanced civilization would face constraints, enormous energy requirements, stability problems, causality paradoxes, and the vastness of space. This suggests a universe where civilizations can arise and advance technologically, but their expansion is constrained by physics and practicality. They remain largely isolated from each other. Contact between civilizations is rare. The cosmos is not full of bustling interstellar empires, but rather sparse civilizations separated by vast distances. This picture aligns with observations. We see no obvious signs of advanced alien activity. The cosmos appears quiet and ancient, not actively engineered by intelligent beings. If advanced aliens exist, they might be limited by the same physics constraining us. They might long for faster-than-light travel as much as we do. But wishing for it and achieving it are different things. The universe has fundamental rules. Advanced civilizations must work within those rules. That might be the most important lesson. We're all subjects of physics, all constrained by the nature of reality, all limited in what we can achieve. Understanding these limits helps us think realistically about the cosmos, our future, and the possibilities for contact with other minds. Let me add one more perspective. Comparing faster than light travel to other advanced technologies that seem possible but face practical obstacles. Consider fusion energy. We've known how to create nuclear fusion for decades. Fusion is theoretically possible. The physics is understood. Yet practical fusion reactors that produce more energy than they consume remain elusive after 70 years of research. Similarly, consider molecular manufacturing or nanotechnology. We understand the theory. We can manipulate individual atoms. Yet building complex structures atom by atom remains beyond current capability. Or consider terraforming. We could theoretically transform Mars to be habitable, but it would require centuries or millennia and enormous resources. These examples show a pattern. Technologies that are theoretically possible face enormous practical obstacles that delay or prevent their implementation by centuries or more. Faster than light travel follows this pattern. The theory permits it in some formulations. But practical obstacles, energy requirements, stability issues, causality paradoxes might prevent it indefinitely. An advanced civilization might understand the theory perfectly and still be unable to build working faster than light systems. This suggests something profound about technology. Advancement doesn't overcome all physical barriers. Some barriers might be inherent to physics itself, not just to current technology. A civilization millions of years advanced might still face the same obstacles we do. That's both humbling and liberating. Humbling because it means even infinite advancement has limits. Liberating because it means we're not uniquely constrained. All civilizations face these limits. The universe isn't hiding advanced alien visitors from us due to some conspiracy. They might simply be constrained by physics like we are, unable to achieve faster than light travel despite wanting to. If they tried and failed to build wormholes or warp drives, they'd remain in their home star system or region of space, separated from us by light years and thousands of years of travel time. This might be why the universe is so quiet, not because intelligent life is rare, but because advanced civilizations are isolated from each other by the fundamental structure of space-time. They developed intelligence, built civilizations, perhaps reached impressive technological heights. But they couldn't overcome the vast distances and fundamental physics limiting travel between stars. Each civilization is alone on its world or in its local region, looking up at the stars, wondering if anyone out there is looking back, but unable to reach across the gulfs between. That's perhaps the truest picture of what the cosmos might be like. One final observation. The question itself reveals something about human nature and our relationship with technology. We're drawn to faster than light travel. It captivates our imagination. Science fiction explores it endlessly. We dream of starships that can cross the galaxy in days or weeks, but this dream might be fundamentally limited by physics. That's okay. Not every dream is realizable. Some limitations are inherent. Accepting this limitation doesn't diminish wonder or curiosity, it redirects them. Instead of dreaming of crossing galaxies instantly, we can appreciate the vast distances as they are. We can marvel at how much universe there is, how vast the scales, how deep the distances. We can think of other ways to explore and understand. through telescopes, through simulation, through patient light speed travel that takes centuries or millennia, we can imagine building megastructures around stars, establishing orbital colonies, creating artificial worlds within our solar system. We can focus on deep questions. How did the universe form? What is consciousness? Are we alone? These questions don't require faster than light travel to explore. And if other advanced civilizations exist out there, constrained by the same physics, the same vast distances, the same fundamental limits, then we share something profound with them. We're all subjects of a universe with limits, all constrained by physics, all trying to understand what's possible within those constraints. That's a humbling and beautiful thought. In the end, the question of whether advanced aliens could travel faster than light comes down to understanding the fundamental structure of reality and the limits of what physics permits. The universe has provided us with a beautiful set of laws that permit complex structures, life, consciousness, and technology to emerge. But those same laws set limits. Causality matters. Energy conservation matters. The speed of light matters. Whether faster than light travel is theoretically possible or fundamentally forbidden, the practical obstacles are vast. And perhaps that's how it should be. The cosmos is vast for a reason. Distance and time maintain separations that protect civilizations, maintain mystery, preserve uniqueness. We'll probably never know for certain whether advanced aliens could travel faster than light. But contemplating the question teaches us about physics, about technology's limits, and about what might truly await us among the stars.